I spoke about before, but now we have more complete data sets and a more complete picture I'd like to share. And the other topic is on the optical nano imaging of twisted graphene. So the first topic is collaboration with Jim Hone and Cheng Tan, who was a student with Jim Hone, is now at Intel, and ex-postdoc in my group, Jumbo Jin, who's now in Beijing, and collaboration with Justin Song. So in certain circumstances, materials can have a Hall voltage without magnetic field.
If I can just interrupt. So you've got
yes.
something, a window that says no build effects. It's on your screen, it's on your computer, not on ours. Can you see it on your screen? TBT animation. It's probably something to do with the video you've been.
Okay.
Order.
Let me just start the sharing again. Let me try to do it without the animation. Okay, how is it now?
Still there. Blots out just in song, unfortunately.
That's weird. So that means you don't see the slide, actually.
So at the moment, we just see you. Someone just said in the chat, you just need to close the build. I don't know how to do that.
Yeah, I don't even see it.
I know this bug, you just have to close the small build order window.
Let's see, so
Can you see order window?
No, I don't see.
You don't see it.
Here, if I swap this place, wait. Now it's still there?
Yep. Doesn't matter. We know we've seen Justin somewhere else. Right. If there's anything really important on the bottom right hand, try closing Keynote.
Oh, wait.
Good. I think it's gone now. Are we starting it?
And now?
Good. Very good. It's gone. Thank you.
Okay, very good. So, sorry, 1 second. Okay. Now, in some materials, you have a Hall effect that usually takes place in a magnetic field, but you can have it without magnetic field. So Hall effect basically means I have an electric field that drives electrons, but the electrons move not only in the direction of the electric field, but can also bend to the left or to the right. Typically, this happens in magnetic fields, but in some materials, this happens without magnetic fields. And this is something that we call the anomalous velocity. And you can see here the equation, which is basically a electron velocity that is perpendicular to the electric field and is driven here by this constant here, which we call the Berry curvature, which is an intrinsic material property. And some materials can exhibit this Berry curvature, and that's what I will explain right now. So let's take a step back and understand what is the effect of a magnetic field on particles, which we all know, but we're typically used to the classical picture, which is the Lorentz force. But in a quantum mechanical picture, we can also represent the magnetic field in a simple way, just by considering here the vector potential. And this vector potential can then translate to a quantum mechanical phase that a quantum mechanical wave function can be picked up. So the wave function that you see here over time then picks up this phase here, EI phi, and usually you don't notice any of that. But if you now have, for example, an electron that makes a loop, it does actually experience this phase. Or if you have two electrons that move together in a magnetic field and then interfere, then this phase is experienced. And for example, the Aharonov-Bohm effect is an example there. But also, if I describe now the electron as a wave packet, okay, then actually the wave packet motion can also feel this phase. And this wave packet will actually bend to the left or to the right, depending on the magnetic field. And in that way, it's actually quite nice to see that you can describe entirely the effective magnetic field just by a quantum mechanical phase. Now, in a material, you can describe also electrons in a wave function, of course, but there we have to use the Bloch wave function that is described over here, and there's always a phase factor as well. And this phase factor is also important. And this can, of course, occur due to magnetic fields, but can also occur internally. And this is what we call the geometrical phase. And this here, for simplicity, I use the same constant A. So we can now represent here this factor A also with the same equation as we used for the magnetic field, as for the vector potential, and relate here this geometrical phase to the constant that we call Berry curvature. So in that way, you can actually see that if you have this internal geometrical phase, you can have also a velocity that's perpendicular to the electric field. Now, keep in mind here that there are small differences here, and typically we represent here the Berry curvature momentum space, while magnetic fields we can work in real space, but the effects are very similar in the sense that you can have a motion perpendicular to the electric field. So if you now look at this motion for these two contributions, so we have again the magnetic field and also the Berry curvature omega. The equation of motion is shown over here, and the velocity here, a derivative of the vector r, is then proportional here to velocity cross product of omega. So this shows you this anomalous velocity, and then for completeness here also have equation of motion here for the effect of the magnetic field. Okay, so now the question is, when does this happen? When do you have actually a relevant omega, a relevant Berry curvature? And so for that we can look at different kinds of materials, and we always like to look at two-dimensional materials, which in some cases they exhibit this Berry curvature. And one example here is transition metal dijacogenide. And in color here, I represent this Berry curvature. And you can see that this actually changes sign. So for electrons, it's the opposite sign from the holes. But also if you go to different valley, it also changes sign. And if you compare this now to graphene, there's actually a big difference. In graphene, there's actually zero Berry curvature. And so why are these two so different? The reason is that in the case here of transition metal dijacogenide, there is an inversion symmetry broken. So it's not inversion symmetric. It's just because on the honeycomb lattice, you can have two different types of atoms. Then if you have inversion symmetry, the Berry curvature disappears. If I take now bilayer graphene, also the Berry curvature is zero. But if I apply an out-of-plane electric field, then I can break the inversion symmetry. And then two things happen. So the out of plane electric field opens a small band gap, but also it then increases the Berry curvature. And as I will show you, this Berry curvature can be very large for small gap. It goes to zero at zero gap, but then at small gap, it's very large. And then when you increase gap, it becomes smaller again. So so in that sense, bilayer graphene is very interesting material for studying effects of Berry curvature. And then from this, you can also have other effects like chiral plasmons that were predicted by Justin Song and also Tony Lowe. So let's put these things now together here, because something that I mentioned already is that you have a cancellation of sign. So there is an issue here that electrons can live in the two valleys. And so effectively, when an electron is living in one valley, it goes to the left, it lives in the other valley, it goes to the right, and the effective average is that it's zero. Okay, so even though the system has a Berry curvature, if we integrate over the two valleys, then the effect is zero. So how do we actually now then measure this Hall effect? And there light comes in. So we basically valley polarize the system with circular polarized light. We pump electrons in one of the two valleys. Okay, so here shown in red. And then only electrons that bend in one direction are then present in the system. Right, so we need to really do two things, right? So we need to break inversion symmetry, which is to apply out of plane field, and we need to shine circular polarized light. Here, that is schematically shown again. So these are the two valleys of bilayer graphene. I pump one of the two with circular polarized light. And I like to refer here this paper by Justin Song that is basically showing a calculation of the Hall effect, so the Hall conductivity, when you shine circular polarized light on the system. So the more carriers you pump in one valley, the more Hall conductivity you get. But the other thing that you see very clearly is that the gap is important. Okay, so if the gap is small, you have 10 millielectron volt, the effect is very strong. If the gap is large, the effect is very small, right? So here you see again, and that's related to the Berry curvature as a function of gap size. So it basically grows for smaller gap size, and then exactly zero gap, boom, it jumps to zero. Now, people have measured for a long time the effect of valley currents and valley Hall in different kind of systems. First, it was done in a system with quite a large gap of 2 electron volts. It was done in MOS2, and the effect is extremely weak. So the Hall conductivity is something like 0.0001 e square over h, that's a -4. And also a lot of scattering in the system, and there's even debate if actually this is a real valley Hall effect or if there's indirect scattering effects happening. And the second set of experiments was not driven by optics, but was driven by pure transport, and their non-local measurements were done to measure the valley Hall effect. And this is done by taking a Hall bar, you drive current in one direction here, and you measure the voltage somewhere here. And then in one of the two valleys, electrons go to the right in one valley, electrons in the other valley go to the left. So that can basically then build up a valley polarization here that can be measured with the voltage, because also here electrons will go more to the right than to the left. So these non-local measurements are actually quite debated, and recently several papers came out. First of all, theoretically here, the papers by Stefan Raj that says that non-local measurements can also emerge. The non-local voltages can also emerge even if there's no topological origin, if there's no Berry curvature effect. And then there was this Nature paper by the same authors as from this paper that actually claimed that you can have also non-local voltages even from non-topological edge currents, because the edges of graphene or bilayer graphene can be quite dirty and lead to edge current flow that can give rise to the voltage that happens on this side. So, so we like to do a much more direct measurement of the Valley Hall effect by shining circular polarized light. And these are the type of bilayer graphene devices that we used. So here you see one, here you see another one. And this is encapsulated in boron nitride. Then there is a graphite back gate, okay? And then there is another top gate that's made out of graphene. So in that way, we can change the doping. But we can also apply an out-of-plane field and open a band gap. So and that band gap is also basically directly creating an inversion symmetry breaking. That then also leads to the Berry curvature. Now let's have a look at the data. So this is the transport through the device as a function of the two voltages, top gate and back gate voltage. And we can indeed see that there's a range here where the current goes to 0. That's where the gap is present. So you basically need to have opposite voltages on the top and back gate. You can see that better here. What is important here is that the gap is very clean. You can see that better here when we measure the resistance of the device as a function of carrier density, then the impedance goes to giga ohms. Okay, so that means there's a real good, well-developed band gap. Now, when we shine light on the device, it becomes conducting because we are pumping carriers in the system. Okay, so in the dark, you see here that there's almost no current. When you shine light, there's a current flowing. This is exactly what we probe here. It's the photoconductivity, okay, as a function of circular polarized light. And we can measure that as function of laser spot position. And so when we just measure the photoconductivity, that's the left plot here, as a function of laser spot position, you can see this happens from the bulk of the device. But now when we measure also the Hall voltage, we also see that there is an effect when we plot the left polarization minus the right polarization, we see an effect. Okay, so usually this should be 0 because there's no magnetic field, so there should not be a Hall effect. But here we do measure a Hall effect. And now we can map out this Hall effect as a function of different parameters. So we can measure it as a function of gap, and we can measure it as a function of carrier density. That is shown here in this graph. So on the left side is the normal photoconductance that as a function of gap and carrier density. You can see that when the Fermi energy is inside the gap, there's indeed photoconductivity. But now the Valley Hall signal shows two resonances here at small gap and also at very large gap, but somewhere in between it's very small. Now let's study this a little bit more detail, but let's first make sure that indeed this is consistent with Valley Hall effect. So we can indeed see if we change the polarization, it makes this oscillatory movement that shows that there is a Hall voltage when we shine circular polarized light. When we shine linear polarized light, there's no Hall voltage, and then change the sign. We also see that when we pump more carriers, there's a stronger Hall conductivity, which is also consistent. And that's consistent here with the theory work. But now let's have a look in more detail when we change what happens when we change the band gap and when we change the carrier density. So first of all, changing the gap size. Okay, so when we change the gap size, we basically see that the Hall conductivity is 0 at 0 gap. Then we open a small gap, then it shoots up, and then it increases rapidly. Okay, and that's also what the theory predicts, and that's perfectly consistent here with the Berry curvature and bilayer graphene. Here it's shown in a color plot. So it's strongest near the band edge, and then it decays away from the when you move to higher Fermi energies. The other thing that is interesting is actually when we change the Fermi energy, so we can basically with a gate also move the Fermi energy up and down. And then we see a non-monotonic dependence here in the experiment, the red curve. And that can be understood also in theory here, the blue curve, you see very good agreement. And an intuitive picture here is that the bilayer graphene has actually quite a complex band structure. It's not just one cone, it has actually a Mexican head structure. You can see it a little bit here in the scalar plot. And the Berry curvature has this equation here, which is a non-monotonic dependence on momentum or electron energy. And so we can directly map out basically this entire map of Berry curvature as a function of gap and carrier density doing this experiment. So as far as I know, that's the first measurement that really maps out these topological properties in bilayer graphene. We can also do this in a 2D map, but I think I will skip this now for the sake of time. Just wanted to emphasize here how strong this effect is. So we see in Hall conductivity that's around 0.04 E squared over H, which is quite large and is reaching, it's not yet at the unitary limit. The unitary limit will be E squared over H, quantized value. But it's 4 orders of magnitude stronger than what was seen in semiconducting 2D materials, where Hall conductors of 10 to the minus 4 was measured, but with 100 times more power. So in the future, we want to also use this to introduce, for example, plasmons that are non-reciprocal that have been predicted also by Justin. Now I want to move to the second part of my talk, which is the nano imaging of twisted graphene. And there's a collaboration with PISA, Marco Pellini, and Pietro Novelli. People from my group here are listed here. Niels Hesp, who just finished his PhD. And so the workhorse for this experiment is probably a technique that all of you know, is near field imaging, which is measuring scattered light that comes from an AFM tip that is illuminated by infrared or terahertz light. But we combine this also with what we call photocurrent nanoscopy, where we measure also at the same time the voltage across a device while we illuminate it with this near field tip. Now, these experiments were initially done with the normal, room temperature SNOM from NEA spec, and we modified it in order to do this nanoscopy. But I will also present some data that are taken here with the cryogenic near field microscope. It's called the cryosnom. You can see here a picture. This whole chamber here is in operation mode, is in vacuum and at low temperature, reaches around 6 Kelvin. Experiments are typically done at 10 Kelvin. This is the parabolic mirror. Here's the AFM tip. A sample is mounted somewhere here. All of this is inside a cold shield that is shown here. That's basically then defining the vacuum chamber here. And then this entire system is on top of springs that you see here that are damping the vibrations from the cryocooler. And the data will show basically a mix. Some of them are taken at room temperature, some of them are taken at low temperature. And this system is mostly operated now in photocurrent mode. So this mode here, when we illuminate with the tip and infrared light or terahertz light locally, and then we measure the voltage across the device. So first we apply this to very small twisted graphene. So when you twist graphene, you can get when you twist graphene, you can get domains. These domains, they can be quite large. They can be hundreds of nanometers or even microns in size. The smaller the twist angle, the larger the domains. But also some reconstruction can take place. So if you take the two lattices without the reconstruction, it looks like this. So you get a hexagonal pattern. But if there's a reconstruction, then actually a triangular pattern emerges. And that is because the atoms like to reconstruct such to minimize their energy, which is actually the AB or BA stacking configuration, which means that the atoms on top and bottom layer are not on top of each other. Now, when we measure this with a photocurrent nanoscopy, we get an image like this. So here, so on the left side is the device. These are the contacts. And then when we scan the tip over the system and we measure the voltage, we get a photocurrent map that is showing here. And this shows different colors. Blue and red, you can actually see a pattern here. And if you look carefully, you see triangles where the sign changes at the edges of these triangles. And these repetitive patterns here, these represent the domains. So that's basically a triangle like shown here schematically and here as well. And if you look here to the left, you see that these domains are smaller, and that means that basically there are different twist angle variations in the device. Now, if we measure this near-field photocurrent map for different contacts, we see also that the shape changes. And it's triangles that have the shape of a triangle over here on the left. But if we now measure between these two contacts, we see actually a more funky shape that initially was very surprising to us, but we can fully understand this. And I want to explain that now, how that works. So first of all, why is there actually this response? This can be understood from a photothermoelectric effect, which is basically understood from the light under the tip heats up electrons, and that heat then through the Seebeck coefficient leads to a photocurrent. And this photocurrent is then actually expressed in this way. Okay, so this equation that is rather simple, but let me explain it in a little bit more detail. So first of all, we need a Seebeck coefficient, and the gradient of the Seebeck coefficient is shown over here. And the reason we need a gradient in Seebeck coefficient is actually simple to see. So let's say the Seebeck coefficient is uniform, and I create locally a heating, then hot carriers can move to the left and to the right, and they cancel out. But if there's a gradient in Seebeck coefficient, then effectively this can generate a current flow. And the direction of the current flow is actually defined now by another gradient here that is represented by the field lines of the current that flows between two contacts. So basically, the way we understand that now is that we have to look at the current flow pattern between two contacts. So let's take contact 1 and 3. There's a flow pattern here, that's these red lines. And then we have to project that on the gradient of the Seebeck profile. Now you can look here at the bottom picture. So these show the Seebeck coefficient of this twisted graphene. And for the sake of simplicity, we model it as dipping at the domain wall. So that's the yellow, these are the yellow lines. That's where the Seebeck coefficient is reduced. And now when the current flow lines are perpendicular to these lines that define the Seebeck coefficient, then you get a maximum signal. Okay, and that can be seen with this equation here. And if it's parallel, then it minimizes. So that means also that if I choose a different contact, I get a different near field profile. And that is shown here. So on the right side, we calculate, we model this system for these contact configurations and these contact configurations. And you indeed see here that the model reproduces very well here, this profile that I showed you here. I forgot to put them next to each other. You can see this one, you have to compare to the model here. So this is very well understood and it's quite nice. And what we learn from this is that we actually, within a Moiré unit cell, we can really image with this nanoscopy technique, we can really image the photothermoelectric properties. Now we move to magic angle graphene. So magic angle graphene is typically at an angle of around 1.1 degree. And that is where the band structure of graphene completely changes. And it has become famous, last few years because of the emergence of superconductivity, magnetism, quantum anomalous Hall effect, and all kinds of fancy physics. And the reason that these emerging phenomena occurs because the Fermi velocity of the electron slows down, and that basically means the bands flatten. So here you can see the band in magic angle graphene, it's almost completely flat. And then there's an excited state here at around 100 milli-electron volt. You can optically excite between these levels. That is what I'm going to talk about. But before doing so, I want to mention here that if you now look at this system and you change the Fermi energy, okay? So I go from basically here from the flat band towards this gap. So I move the Fermi energy from here until the gap. What I see in this Seebeck coefficient is that there is a sharp peak here and also on here. And this happens at something that is called full filling. So that means that's when I put one electron in each Moiré unit cell. And that's basically when these bands here, the flat bands, are completely filled with electrons. This is something we can directly see in the experiment. So now I'm going to look again at this photocurrent mapping, like I showed you before, but now for magic angle graphene. So I show you here this map on the top for different carrier density. And what you see is actually kind of a mess, right? So it looks complicated, different colors, and then when we change carrier density, you see different profiles. But if I now just take a line cut, here this black line, so that's X tip, and the vertical axis is the carrier density, okay, so the Fermi energy, then I can actually see quite a clear profile. So I see some sign changes and stuff happening here, but I see very strong photoresponse here at higher density, 8 times 10 to the 12, and also negative, okay? And actually that makes you think of this graph here, where at full filling here, there is this peak and dip in the Seebeck coefficient. We can measure that for each tip position, and you can see this peak is still there, but then for some tip position, it starts moving, and at some point it disappears. And that's actually quite nice, because this represents locally the Seebeck coefficient as a function of carrier density, but also the shift of this peak is now representing a change in twist angle, okay? Because the full filling condition depends on twist angle, right? Because the Moiré unit cell changes, and I change twist angle, so also the number of electrons that fit in one Moiré unit cell also changes. So this twist angle varies here, and I can follow that basically with this measurement. We can plot now actually the Seebeck coefficient for different tip positions that is shown over here. So indeed, this red curve shows like a peak and a dip. And then for different locations, it looks a little bit more complicated. And that is because we are actually not only probing locally the Seebeck coefficient, but we're probing gradients of Seebeck coefficient. So by some more deconvolution technique, we can then estimate the twist angle from these different locations and make a simplified model that gives you then a twist angle map. That is shown over here. So there's still preliminary data, there's still ongoing work, but I wanted to share this with you. These data are also taken with the cryogenic near field microscope, because you would never see, these sharp features at room temperatures. You really need to go to low temperature to see this. And I think my time is almost up. So in magic angle graphene, if we do scattering SNOM, we also see plasmons. It's something I have presented before already, so I just mentioned it very briefly. These are collective excitations that emerge even in undoped twisted graphene. So initially we were thinking of the regular plasmons, but that's actually not the case. These are different kinds of plasmons. Still, when we change the excitation energy, they change wavelength, so they make you think a lot like regular plasmons. We can see them in different samples. But we're actually pretty sure that this is not related to the regular plasmons, because if we measure this now with terahertz frequencies, we can see that there's almost no signal. So there is not really a Drude response in the signal, in the system, which is also logical because it's an undoped system. But the physical interpretation here is that these are actually interband plasmons. And the way you can actually see that is that, let me actually go back to the band structure. This is the band structure here. So I'm actually exciting carriers from this band to this band. Okay, so it's an interband transition. And also that can give rise to a plasmon. Usually in systems, those plasmons are very lossy and exist at very high energy. But here with twisted graphene, they can exist at lower energy, even at 100 millielectron volts, so IR frequencies. But they can still propagate. There's a little bit more subtle why they propagate, but it's related here to the strong oscillator strength between these different levels, because they're quite flat. A simpler picture to think of this is basically that electrons in this Moiré unit cell are shaking. So electrons are quasi-localized in this triangular lattice. If they shake in real space, the quantum mechanical picture is that just the wave function becomes like a ring, and this breathing of the wave function is like can also become a plasmonic mode that can propagate. When we look at the plasmon dispersion energy versus wave factor, we also know for sure that this is not a regular plasmons, because if we extract now the conductivity from this plasmon dispersion, we find that it does not fit a Drude response. But if we fit now an interband resonance, shown here as a simple expression of the conductivity, we can express this as an interband resonance, we find a good fit. And so we can understand this from this interband transition that is shown here with these arrows. Okay, so I want to skip then this large part, because we're doing now also some ongoing experiments of twisted graphene and light on boron nitride. It's interesting because then an additional superlattice appears. And that is also something we can see in near field images. So we can see another periodicity appearing that is very large, can even have micron size. And this is still ongoing work. So I want to wrap up. And if anybody wants to discuss this last topic, I'm happy to discuss in person. And with this, I want to thank you for your attention, and of course acknowledge all the collaborators and funding sources. Also advertise here this postdoc position that is available, so please contact me if you're interested. Thank you very much.
Great, thank you very much, Frank. I'm afraid we're a bit pressed for time, but maybe there's a question. Hopefully there's a question here from the audience. Not. Yeah.
Hi, Frank. Thanks for the very clear and nice talk. I have a question on the fulfilling condition that you show on the photocurrents.
Yeah.
This is at very low temperature, so it's at 10 Kelvin or 6 Kelvin, right?
6 Kelvin, yeah. So at 6 Kelvin, These data are taken.
Mhm. Did you measure as a function of temperature how this condition is changing, if it's shifting from the full filling condition or not?
Yeah, we have a temperature dependence. I don't think I have it here on this slide, but basically this peak starts to smear out more and more. And at some point it completely disappears.
Okay. As expected.
Yeah, because these flat bands have a bandwidth of just a couple of milli-electron volt, right? So when you are at room temperature, this effect is completely smeared out. The way you can also see it is that here you have a gap, right? So basically this is the fact that you're entering a gap. This gap is shown here in the band structures, this gap here. And this gap is on the order of, 5 to 10 milli-electron volts. So at room temperature, you will not see that.
Okay, I'm afraid we're going to have to move on. So thank you very much again.
Thank you.
So the next talk will be given by Pablo Alonso Gonzalez from Oviedo. If you can't hear him, or if there's something wrong with the sound, please shout out right away, just wiring him up. Okay.
Okay, so thanks a lot for the nice introduction, and I want to thank also Luis and Alexei for giving us the opportunity to show our latest results here in this conference. The talk that I'm going to present is going to be focused on two main results that we have published during this last year. They are shown here into these two images. One is this one, which I will try to explain you that this is a lens where polarityns, in this case phonon polarityns, can be focused to these subdiffractional areas like this one. This occurs with these phonon polarityns in a peculiar way because they are shown here, they are hyperbolic. So they propagate in a rather special way. They are very directional. This changes a little bit the understanding that we normally have of refraction, for example, or reflection. All the fundamental optical phenomena changes a little bit when we have this highly anisotropic media. And the other result that I will explain is this one. And in this case, we are also doing focusing, like you can see here, a spot. But in this case, it's not based on a lens like this one, which is based on refraction, but it's based on a launching or antenna effect from this kind of metal pads that are here, but also can give us really tiny spots. So we can, let's say, as the title says, manipulate light at the nanoscale with this media, right? So we can do some functionalities like lensing or focusing, which open us some possibilities to do nanophotonics at the infrared frequencies. At these spectral ranges, we have many absorption from molecules and other objects, and then we can think of well, some sensing devices or other possibilities like thermal management and so on. So I will start just with a very brief introduction to phonon polarityns, because yeah, maybe in this conference it's not needed, but typically people, when we discuss polarities, they are all thinking on plasmons. But later during the last years, phonon polarities are getting more and more known. But still, I want to do a very small introduction, and then I will also explain a little bit about the hyperbolic propagation of phonon polarities, why they are so special, and finally these two results that I already mentioned in the first slide. So let's start with this introduction. Very simply, you all know what the plasmon is, so I will not repeat this. Basically, we have a medium where the permittivity is negative, surrounded by a medium which is positive. It is negative because the permittivity, so it's negative, so it does not allow a field to enter. And in this case, it's because free electrons are screening out the field, right? And by screening out the field, surface wave solution of Maxwell equations arises, and this is the plasmon polariton when this material is shined with light. So the properties of plasmons are these, or so these are good properties and bad properties, let's say. So the good things about plasmons is that the deep subwavelength confinement can be achieved, and they exist in a broad spectral range. But they also show, let's say, drawbacks like the short lifetimes. Electron-electron scattering is very important in this media, so lifetimes are typically in the range of 10 femtoseconds. And there are other, let's say, drawbacks like the lack of active tunability. On the other hand, phonon polarityns are a similar solution of Maxwell equations, but this is triggered by again by a negative permittivity, but in this case not because of electrons that are screening out the field of the material, but by lattice vibrations. So in the infrared spectral range, there are, let's say, in polar materials, there are, let's say, dipoles in the surface due to the crystal lattice that can screen out this field, giving rise to this surface wave. Maxwell equations, same solution, everything the same, but in the infrared spectral range. The good thing is that now electron-electron scattering is not so important. Now it's phonon-phonon scattering. So in this case, the lifetimes of phonon polarities is much longer, can reach 1 picosecond and even longer. The bad thing is that the broad spectral range of plasmons is lost, and now this negative permittivity in the infrared only happens between TO and LO, the optical phonons, transversal and longitudinal. So we are restricted to narrow spectral ranges. But and also they have the lack of active tunability, although we can change the thickness of the, I will show you that we can change the thickness of the material, and that way you can change the dispersion, but it's not active. Well, there are solutions like combining it with graphene, which can solve this problem. But yeah, these are the main characteristics, let's say. And the first studies were done in silicon carbide, quartz, and so on. Now we are coming back to these materials. So the first studies mainly triggered by Rainer, also Professor Gefet on silicon carbide. But then later, or during the last years, this field moved to the van der Waals materials because they offer us materials that can be nicely engineered, and they also support phonon polarityns. But now we are coming back again to bulk materials like calcite and others that you will see in the literature soon, because they have phonon polarityns with really nice and unique characteristics. So as I said, from these bulk materials that are difficult to engineer in some cases, we went to van der Waals materials, and there the first one was HBM that was demonstrated to have phonon polarityns. Like 2-3 years ago, we found another material, and this I move to the next point of the talk, which is related to phonon polarityns in alpha molybdenum trioxide. So we found that this material that was reported before that it can support phonon polarityns and so on. It's a very anisotropic material. It has an orthorhombic crystal structure. So the lattice constants along the 3 directions of the coordinates, spatial coordinates, are very different. Because of this, when we do typical experiments, non-experiment or polariton interferometry experiment, so we come with a Snom tip and we launch, we can beat this momentum mismatch with polarityns, and we can launch these polarityns. Polarityns propagate, they need to reach an edge, and they come back to the tip, so we can measure interferometric signals. We did this experiment on molybdenum and trioxide, and we saw these patterns, particularly in what is called their lower Reststrand band here. We can see that the phonon polarityns only propagate in one direction and not in the other one. So it's super anisotropic, right, in the plane. So to study this effect, we did circles. So we could probe how the polarityns were propagating on different directions in the plane, and try to see how let's say the anisotropy was revealed in this way. And we saw that in some Reststrand bands, so where they exist, we have this kind of ellipse behavior, and in some others, like the one that I showed you before, where there was only propagation in one direction, we have this almond shape. If we take the Fourier transform of these near field patterns, we can get here the isofrequency curve. What is called the isofrequency is for a fixed frequency. We can go to momentum space, and this is called the isofrequency curve or contour. And here we can say that in one case they are elliptical, but in the other case they display a hyperbolic curve. And this is why these phonon polarityns are called hyperbolic. And why is this interesting? Well, first of all, let's say that these polarityns are very interesting also because the lifetimes that we saw in this material are record high. So we can reach 8 picoseconds, and even we have some flakes where this could reach 15 or 20 picoseconds because losses are really, really low in this material. So, but what is the cool thing about hyperbolic media? That it makes it interesting to work with and to try to understand fundamental optical phenomena like refraction, for example. It is that the K momentum vector here and the Poynting vector S are non-collinear normally. So in this isofrequency curve, if we move from the origin to the curve, we have all Ks that are available in this material. And because we have an asymptote here, we can have many different Ks and all very large. This gives the possibility that in this material one can launch or we can support extremely high density of optical states. And this is important for, well, light matter interaction studies and so on. But on the other hand, this non-collinearity also gives rise to very peculiar effects, right? So normally we are used to work with isotropic media where K and S are parallel, plane waves, normal plane waves, where K vector is perpendicular to the propagation direction. But in this case, it's not happening this way. Okay. If one goes to the real space, this is what happens. So we have a wave that propagates, but in this case, the energy that, for example, in this part of the wave, because in the middle part of the wave, K and S are parallel. You can see here that if energy goes in this direction, here the K, the wavefronts are perpendicular to the direction of propagation. So K is collinear to S, but in this other part here, this is not the case. Here, S goes in this direction, but K, which is perpendicular to the wavefronts, is almost perpendicular to the energy direction propagation. So this is peculiar, right? And what we wanted to do is, okay, let's try to understand what happens with refraction in this case. Very simple physics. The Snell's law. We studied this probably in the first course of our bachelor degree. Here we see that when light enters into a media with a different refractive index, in this case larger, so we can see that the light bends towards the normal. So it's closest towards the normal, and this gives us this typical effect that when we put a pencil on water, it bends, right? Okay, but we can see this effect not only by looking at the equation, but from where this equation comes from, and it comes from momentum conservation, as usual in all these equations. Well, what is this? This is just that the momentum of the light has to be conserved along the boundary. Once it is incident and what is refracted in the other medium. So this vector has to have a projection on this boundary equal to this other vector, which is the light entering into the other medium. So these two vectors needs to be equal. This can be seen not only in the real space, but in the momentum space with isofrequency curves as before. In this case, this is isotropic media. So we have two circles where K can take any direction. but they have different diameters because we have different refractive indexes. That's it only. Okay, the velocity of the light is different in both cases. So in this case, we have the boundary, and the projection to the boundary in this case is the same as well. So this is the case that is explaining. Yeah? So if we have this incident vector, by having just this other medium with this other circle, we have this boundary, and we just have to take the vector that crosses this outer circle, giving rise to the same projection that the first vector. And then we have momentum conservation, and this is the solution of refraction in isotropic media. Very simple graphical method to see. But what happens now? You have a hyperbolic medium. So we saw that we have polarities in this hyperbolic medium. So we were interested in this. Also trigger questions before theoretically. So what happens if we have, instead of isotropic media, hyperbolic medium? So instead of having now the circle around, we have a hyperbola. Okay, let's take a hyperbola that has crosses at the boundary at the same point that before it crosses the circle here. Okay, but we take the same hyperbola. So K can take the same vectors than before to reach momentum conservation. So we have the same K vectors here. The K is going to be like this, and K is like this, like the red arrows. But what happened with energy now? Energy now goes in another direction because it's perpendicular to the isofrequency curve. So the result is that we have negative refraction. This is the effect of negative refraction in a hyperbolic medium or highly anisotropic medium. This has been predicted for years and also measured at microwaves, making metamaterials basically. So one can make a hyperbolic medium out of an isotropic medium by just making a metamaterial. This is interesting because there have been many theoretical works where they predict that you can make a lens, perfect lens, with a negative refraction. So you have two waves that come to a boundary, and then they can refract negative, and they can focus. Okay, we thought, okay, now we have a hyperbolic medium, but not only one hyperbolic medium, we can have two hyperbolic medium and study the refraction between two hyperbolic mediums. So instead of one circle and a hyperbolic curve, we can have two hyperbolic curves. And we can have two hyperbolic media by, for example, using this MO3, which is hyperbolic, but making some trick to do like two effective media, different effective media, okay? If we do this, there are theoretical works that say that you can go to reach this kind of negative refraction and get really nice focusing, okay? Okay, so we have this material, as I said, where S and K are non-collinear. What we thought is the following. Okay, let's do two effective media by just drilling a hole on the silicon dioxide substrate. So in one case, the MO3 is suspended, and the other case is supported by silicon dioxide. Just by dielectric loading, then we have like two different hyperbolas in this medium. So we can open this hyperbola, green hyperbola, to the blue hyperbola here, in this way, just by doing this trick. So we have two hyperbolic medium, and now we can maybe make this hole in the shape of a prism and study just refraction. So this is what we did. First of all, let me show you what we can expect. So here we have the prism. So if one is able to launch here polarities that go in this direction, okay, let's imagine that this is this direction, and this direction is it corresponds to this S vector here that is black, and here it is collinear with K, with momentum, okay, because I just choose this direction, okay, in this case, in the hyperbolic medium, and this is the only point where K and S are parallel, are collinear. Okay, let's take this one. So if light enters into this boundary, into this, it's in this medium, and it's following these conditions, and now got this wave into the boundary. What happens? Okay, we have the boundary. We put the boundary here in this isofrequency curve like before, and we just need to check what vector that crosses the outer hyperbola has the same projection to the boundary than the incident wave. Very simple. And what we find is this green vector that crosses the outer hyperbola. So it's the wave vector that's available in the other medium. It has the same projection that this K vector that is here, the red one. But what happened with energy? energy here was collinear, but now energy goes in this direction. And this gives rise to the following situation. We have K bending to the normal. K, this is the K out. If we go to the real space, we have this wave entering into the medium, but this is what we have refracted in the refracted condition. K goes or bends towards the normal, as it was in isotropic media, as I showed you before, in the typical case of the pencil, but energy goes out of the normal here, out of the normal, completely out of the normal. So, and this is what is called anomalous refraction, okay? And this is what we try to do. And here we fabricated the device. This, we have the prism. It's just the MO3 flake that is laying here on the silicon dioxide, but here is freestanding. We launch Phonon Polarityns from this side, from the edge. They have parallel K, parallel S. They go to the boundary, and we expect here these vectors, as we saw in the theory. And what we saw with our near field microscope, it was these fringes, and actually you can see here that the energy goes in this direction, right? Because the fringes go in this direction, the maxima of the fringes goes in this direction, but the K vector, which is normal to the wavefronts here, you can see that is bending towards the normal. So we have really visualized this anomalous refraction of polarityns. This is the numerical simulation, and this is well again the projection to the boundary condition and so on. We change the wavelength, and by changing the wavelength, we can make this angle really perpendicular to the K vector. So super perpendicular to the normal of the boundary. Well, this is was the first experiment. The next experiment that we tried was, okay, if we now mirror our prism, we can have a lens. So if in one case we have a refraction and the energy goes in this direction, if we just made the other part of the prism like this, we will have also refraction in this direction, and we can have a focus. And this is what we did in the experiment. We did this prism in the shape of a triangle. Now the wavefronts come here, they refract at these boundaries, they go in this direction anomaly. Normally in isotropic media, they will go in the direction of K, okay? And now they gave rise to this focus. This is the numerical simulation that fits very well with the experiment. The focus that we found that we can reach, it's around lambda incident, which is around 10 microns wavelength, 11 microns wavelength, divided by 50. So it's deeply subdiffractional. And also, if we compare to the polariton wavelength, so here, I don't know where is the cursor here. If we compare to this polariton wavelength along this direction, our spot is lambda polariton divided by 6. So conceptually, it's also subdiffractional compared to the polariton wavelength, not compared to the incident wavelength. Okay, and this is because of the in hyperbolic medium, you can have a really large K in some directions of propagation. Okay, I think, how much time do I have? 2 minutes only. Okay, I will go super fast. So I explained you now one case, which is when K and S are parallel, but the general case of refraction will not happen for this particular case. It happens when both K and S, momentum and Poynting vector, are non-collinear for the incident wave, but also for the refracted wave. That is the most general case of refraction. And this is what I show you here. K is now no collinear with S, and the K out, if we put a boundary like this, will be also non-collinear. And if we do so, we can find a condition where the energy incoming to the boundary does not suffer of any refraction. It just passes through the boundary. So you can see here, S passes through, S out is like this, but K changes. So you can just put a boundary, you just launch a polariton, the polariton will pass through along the same direction, but its wavefronts will tilt according to momentum conservation in these two different media. And we did this, and well, it's kind of difficult to make this experiment, okay? Because we need first to launch polaritons in this edge. They are with K and S parallel. And then we do a first boundary where we change K and S, so they are not anymore collinear. And then we have another boundary and another boundary. So this is a 3 boundary condition, and then 3 refraction process, or two refraction process and a reflection. It's quite complicated to explain in 2 minutes, but you can see here that both in simulation and in experiment, we have a S that is going in this direction that is almost parallel to the S out from the last boundary. So we can see that refraction can give rise to this bending free condition. Okay, and with this, I just go very briefly to the last, to the other result I wanted to show you, that is using antennas. The antennas can launch also polarities. In this case, it is not based on refraction, it's just launching. So we have an antenna that provides enough momentum to launch these polarities. If we change this angle of tilting angle of the antenna, we can find an optimal condition where all the rays launched by the antennas give rise to a focus that can be very small as well. Okay, and this is, we reach also this subdiffractional focusing by doing this kind of devices. Just advertisement of later on, Yahua Duan, postdoc in the group, will talk about twist nano-optics, how we can, by twisting 2 flakes of MO3, we can reach the condition where there is a natural canalization of phonon polarities on the surface, so we can make natural waveguides without etching. And yeah, this is a very interesting. It happens through a topological transition, optical topological transition in the medium. So just I want to thank all the people involved in this group, in this work from the group, Javier Martin Sanchez, Yahua Duan, and the PhD students Javier Gonzalo. Gonzalo is here, and he has a poster on the refraction. So you can also visit this afternoon his poster, and Anna, Abel, and Christian, and also, of course, all the collaborators and funding, and you all for your attention.
Thank you very much. So we've got time for maybe a couple of questions. They're quick. Yeah, but then the other.
Pablo, so in the focusing of polaritons, so do you see the field enhancement in the focus, or is it actually lower?
Yeah. Yes. So indeed, we see a field enhancement if we check it along this direction. But if we go in this direction where the polaritons are launched, as they decay exponentially, right, this spot might have more intensity than the focusing that the focus that is obtained. So if you have two polarities that launch and they focus at one point, the intensity at that point is similar in this case than the intensity of the initial phonon polariton, okay? But the size of this spot is much larger than the one that we have the focus. So in the end, we did also this, for these profiles, we did this profile along this direction, okay? To show that because that way we could measure the width of the focus nicely. The other case, it's like decaying exponential, and then we have to focus as well, but it's more difficult.
I see. And in the case of the negative refraction?
Yes. For this focusing.
Yeah, here.
Yeah. In this case, we did the profile along this direction. And there you can see a nice focus. If you take the profile like this, you see that it's quite intense in the beginning, and then as it is exponentially decaying, it's decaying, and then suddenly we have a peak. But this peak does not reach really much more intensity than the previous one. Yeah.
So it's significantly limited by losses, right?
Sorry?
It's significantly limited by losses.
By losses, yes.
Okay.
You have to take into account that in these refraction experiments, we need a propagating polariton that is already propagating from here, from the edge. So when we are measuring it, it already propagates 5-6 fringes. So we are already in the decay region for measuring this stuff, right? And yeah, this is what it is.
Thank you.
Okay, great. We'll have to move on now, I'm afraid. So thank you very much again. So the next talk is online.
Okay. Can everybody hear me or anybody hear me?
Sorry again?
Are you able to hear me okay?
Yes.
Okay, let me share my screen. And
Okay, we're just setting something up here. Is that right? Okay. Right, well, so the next talk's from Nathaniel Gabor from Riverside. So
Yeah.
again, this, okay, thank you.
all right, thank you. First of all, I'd like to thank the organizers for letting me give this talk. I'm going to talk about something that we've been working on for some time in our lab, kind of slowly and methodically. And it's this idea of using van der Waals materials as what I'll describe are exciton quantum simulators. And I'll explain what that means. And it kind of gives a bigger picture view of something that we're working towards in my lab and many labs around. But before I talk about it, I should thank all the many people involved. Today, I'll be talking mainly about the work of Erfu Lui and Fatima Barati, Trevor Arp. These are former students and a postdoc. But this is work that's been done with many, many other groups and collaborators who've all been kind of instrumental to it. And the idea is that we are using van der Waals materials as a new platform for something called a quantum simulator. And this is not a new idea. The idea of a quantum simulator was described, more than a decade ago. But I think it's a very important idea. And I think many of the talks that we've listened to over this week have certainly applications in this space of quantum simulators. There's a really nice recent paper, if this is new to you in this year, where many of the kind of various members of the community set out to define what we mean by a quantum simulator. And the idea is that it's an engineered, so it's a device where you have a quantum many particle system that you can controllably simulate complex quantum phenomena. So this is not quite a quantum computer. Instead, it's a simulated quantum system where you can solve quantum problems that classical supercomputers really struggle to do. So the second paragraph here kind of sums it up, and it says they have a potential to fill what is right now a very important role. They can be more powerful than a conventional supercomputer, but we don't have to wait for the development of full, fault-tolerant quantum computers. And many different algorithms have been set out for this. Many different infrastructures and architectures have been described. And in fact, in this paper, even the 2D materials community gets a little shout out. We get about a 3-sentence paragraph describing kind of the potential in that space. The ones that you've probably heard of are things like atoms trapped in a lattice, which I'll talk a little bit about, ions trapped in a lattice, and more recently, some newer devices where they're using quantum dots to form kind of small numbers of qubits in quantum simulators. But the idea is that we are not looking to create a quantum computer, but because of all the energy and excitement about quantum computation, there's a lot of overlap in the way we think about it. And in quantum computing, there's a very, very famous set of guidelines. This is from the late 1990s that sets out how we can establish a quantum computer. So what experimentally do we need for a quantum computer? And it's basically 5 criteria. And I'm going to go through these in detail for a quantum computer, and then I'll talk about what these mean experimentally. The first one is a scalable system with well-characterized qubit. I think that's one of the most important things. What is your active qubit? Then you need the ability to initialize many of these qubits in a simple fiducial state. So a state that can be compared as kind of the basis, and then you can look at the excitations of that state. And you need long relevant decoherence times. And this is important for basically initializing a quantum computer. You need a quantum computer that you can anneal faster than the decoherence time of the bits, or else it's just completely useless. You can't do it. And then the last 2 are a universal set of quantum gates. And a key one, I think, for this community, and I'll talk about this at the very end, is a qubit-specific measurement capability. So in a quantum computer, we want to be able to measure every single qubit. Even though you have a large entangled state, you want to be able to process and basically access every qubit. So what does this look experimentally? The history has shown us through the ultra-cold atom community that many of these things are possible. And I think many of us are familiar with this kind of laser trapping of either ions or atoms or now even molecules. And they've achieved many of these things. And they are one of the candidates for quantum computing. But more importantly, they've been able to use ultra-cold atom-based systems as quantum simulators, where they can simulate very unique Hamiltonians that have been well understood and well studied, but not demonstrated experimentally. And if you look at that community, they basically have found over the last several decades, they've reached several important benchmarks in establishing this idea of a quantum simulator. So one of the things that the cold atom community has done very well is create tunable trapping potentials. So they can use laser trapping in these very, very well controlled periodic lattices. They can do 1D, 2D, 3D, et cetera. The other thing that they've gotten really excellent at, which is actually quite a challenge, is getting these traps to have just one excitation per trap. And it's a very non-trivial process to cool the system to isolate a single atom per trap. And then they have a lot of knobs that we don't typically think about in condensed matter systems, like tunable interaction parameters, the ability to control individual qubits with light. And primarily one of the biggest things is being able to measure single excitations with light. So they can actually look at the emission from a single atom. So these are the benchmarks that they've already reached. And I'm going to go through some of these because there's a parallel to what a lot of us have been working on. And some of us have started reaching towards some of these goals. And so we already know about, we've heard quite a lot about these Moiré potentials in 2D materials. And I'm going to argue that through this, we are able to achieve several of these criteria, which puts us kind of in the direction of being able to demonstrate quantum simulators probably within the next decade. And one that I'm not going to talk about, which we have some work, but there was a very nice talk and discussion earlier this week already, is about the tunable interaction parameters. And one example of that is that you can take interlayer excitons and look at their dipolar interactions in these arrays. And so I think this will become probably one of the most important interactions in these systems. But I'm not going to talk about that one because we've heard a little bit already, and I think you'll still hear more in the literature in the coming years. What I am going to talk about is, to start, the first one, which is this idea of having a tunable trapping potential in a periodic lattice. And we've been doing work, and many in the community have been doing work in this material system, MOSE2 and WSE2, and trying to understand the basic properties of the interlayer excitons. And we've recently had some success demonstrating tryons that are controllably trapped in this Moiré potential. So if you take two monolayers of this material, you actually have a lattice mismatch of about 0.1%. And this mismatch is actually sufficient to give you a Moiré potential. So it's not just the twist, but these lattice mismatches can be always very important in getting these kind of Moiré modulations over the sample size. And as many of us know, when you stack these two layers together, you can have different species of excitons. You have interlayer excitons where the hole lives in tungsten selenide and the electron lives in the MOSE2 layer. But you can also have the intralayer excitons that live within each of the layers. And we can separate these spectroscopically. And I'll show later we can actually use some new photocurrent techniques to probe some of the deeper, even more detailed physics of these. Again, as we've seen in the literature, and many of us know, if you measure the photoluminescence as a function of photon energy, you see to the right of this graph the intralayer excitons. So these are the kind of conventional excitons that you would see in an isolated material. And when these materials are very clean, so this is an HBN encapsulated sample with graphene gates, when they're very, very clean, you get very, very sharp photoluminescence lines that correspond to the interlayer exciton. And this particular interlayer exciton is from the K valley in WSE2 to another K valley in MOSE2. And that puts us at an energy of about 1.4 EV. And so in this work, we cooled the system down and we had very, very high quality, very sharp emission lines. And we studied the photoluminescence as a function of gate voltage. And in this first plot, what we show is that, under what I wouldn't say high laser power really, but a moderate laser power, we measure the photoluminescence as a function of gate voltage and photon energy. And we start as a reference just looking at this interlayer exciton emission. So it's this very, very bright emission. But what we found is that below the energy of the interlayer exciton, there were many, many features, which we labeled kind of interlayer exciton 1 minus and 2 minus, when the sample was injected with electrons. So on the electron side, we saw these kind of emission peaks, but also on the hole injection side, you saw these similar basically peaks. And one thing to note about these features is that they don't really disperse with gate voltage. They're essentially steady with gate voltage. In another way to say it is that they're vertical in this plot. Whereas usually what we know about conventional tryons is that they tend to have some dependence on the gate voltage, where they actually have a bit of a bending there. One thing that we found, and this is a really important finding, was that when we go to very low power, these large, broad features that we see actually become very sharp and very numerous. And so this broad PL evolves into these very sharp PL lines under low excitation. And as we learned, this actually comes from the localization effect by the Moiré potential. And the way we have evidence of that, I'll talk a little bit in the next slide. But one of the key things is we can study the magnetic field dependence. And if you look at the G factor, it behaves in a very similar way to the interlayer exciton. And one of the most interesting things is that this kind of sharpening of the features comes from some of the detailed band structure of these tryons, but also from the fact that they are becoming very localized in their trapping potential of the Moiré lattice. And so based on calculations and a lot of other data, we began to understand that even this fact that they don't really disperse with gate voltage comes from the fact that once the tryon is localized in a trap, it no longer interacts strongly with the carrier density bath. So you're able to actually isolate these tryons in their trap, and they essentially become single excitations isolated from the kind of global charge carrier density. And so, you know, the picture that we've given is that we now have these Moiré periods of about 20 nanometers, which are controlled by, in this case, lattice mismatch, and can also be controlled by twist. And this gives you this very, very sharp emission of these isolated tryon features in their interlayer tryons. So they demonstrated a strong dipole moment out of the plane. And we can really begin to understand the properties of the system. And as we know, tryons, one of the big advantages is that we can use electrical control to kind of manipulate these. So we're quite confident that we've now gotten a handle on confining single excitations, single tryons into the traps. And we're going to begin to study how we can tune those trapping potentials. And one thing I would like to say, you know, this came up a lot in discussion while publishing this paper, is that these aren't phonon replicas. I'll actually talk about phonons in a minute. And we can show that there's no such phonon replicas for any of the other exciton peaks. These really are basically new emission lines coming from this kind of mini band structure of the Moiré potential. And so it's really just coming from essentially a zone folding of the band structure that you get from having this new periodicity that comes from the Moiré potential. And so we can show quite clearly that that's the case. And later on, I think we'll show more and more that we can control even this band folding as we can control the lattice, the lattice scale of the Moiré potential. But we now have, I think, demonstrated pretty cleanly that we can trap these things in periodic lattices, and we can start to work with this as our basic excitation. But one of the challenges in cold atom physics is actually cooling the atoms. And we also have some interesting data that's much newer, not yet published, that suggests that we do have some analogies to cold atom physics. And the system we studied here is actually very similar. But instead of monolayers of each of these, we used a bilayer of tungsten diselenide. So this is kind of the intrinsic bilayer exfoliated from bulk tungsten selenide that is then kind of coupled to MoSe2. And we used a new technique that's detailed photocurrent spectroscopy based on supercontinuum excitation. And we studied these devices, and what we found is that they're very, very good PN junctions. So if you think of kind of a conventional PN junction, you can have the interlayer region where the basic excitation is this interlayer, lowest lying interlayer exciton. And the device essentially behaves as a PN junction when you have the chemical potential tuned right into the middle of the gap, just like you would expect. And so we get, if you look at the current voltage characteristics, you get very, very good diode characteristics where the what's called usually the ideality factor in a diode it's very close to 2, which is quite good for TMDs and van der Waals materials. And you get very, very large photocurrents that we studied. And one of the most interesting things we found when we looked at the K to K interlayer exciton, we essentially saw very, very strong periodic sidebands. And these sidebands were separated by about 30 millielectron volts. And you can actually Fourier transform the data to see that these are very, very sharply defined right at 30 millielectron volts. But also in this system, we found a new exciton, a lower lying exciton. And this exciton is actually not from one K valley to the other. Instead, it's from the gamma valley to the K valley in MOSE2. And again, this is a near infrared exciton, so it's near about 1 electron volt. We again saw these kind of 30 millielectron volt separated sidebands. And again, you can Fourier transform the data, and we actually see at this lowest lying exciton 30 MeV, but perhaps a weaker feature at about 20 MeV. And what we understand these excitons is that they come from basically 2 different lowest lying states, but we're doing photocurrent. And so photocurrent essentially probes absorption. So whereas you may not see such strong features like this in, say, a PL measurement, we're probing directly the absorption. And so we can see both the absorption of what is called, the KK interlayer exciton, but also a gamma K interlayer exciton. But on top of that, we're seeing these kind of 30 millielectron volt echoes. And we actually can even look at the device characteristics and see those same kind of oscillations as a function of voltage. And this comes from essentially an interlayer Stark effect. When we apply a source drain voltage, you're basically moving this kind of through a Stark effect through the interlayer electric field. And we see that under kind of an approximation of a dipole moment, which I'll discuss in a second, we see that those oscillations do occur right at about 30 millielectron volts. And so not only do we see these kind of 30 millielectron volt oscillations, we can control them with an interlayer voltage. And from that, we actually get a dipole moment. This is an interesting thing that came up in an earlier talk, is that normally you would approximate the dipole moment of these interlayer excitons roughly on the same scale as the thickness of the device. But from our Stark effect control, we actually find that the dipole moment's much smaller than the thickness of the device. So it's basically a factor of 0.4 or so. So this is an interesting result that we're trying to understand, but we at least now have a handle on this physics. And it actually comes from some very, very old condensed matter physics, or if you'd like, kind of quantum chemistry, where we think about vibronic progressions. And one of the origins of these vibronic spectra is the fact that the exciton actually becomes more localized. And this isn't like a smaller Bohr radius. It means that it's basically the wave functions are becoming more localized. And in localizing, they couple more strongly to vibrations. And so this 30 millielectron feature that we see matches very nicely several Raman modes and calculated band structure of the phonon modes in the system. And what we're seeing now is essentially these sidebands that are often used in AMO physics to cool. You can now think about strategies, and we are thinking about strategies to use these sidebands to essentially cool the excitons into a single excitation per trap. And again, earlier this week, we saw some nice work by John Lupton where he showed very clear vibronic progressions, but in a very different measurement. Here we're measuring essentially absorption and seeing them under really sensitive photocurrent measurements. In his case, he was doing this kind of up conversion process where you would see emission from these vibronic progressions. So the last thing I want to say is that there's, I think, a big future in these quantum simulators. And I think one of the things that this community especially can provide some real strength is in these last two, which are very difficult using far field techniques. What we need, I think, to establish is basically the ability to measure single excitations within a single Moiré potential trap. And if you can do that, then you can begin thinking of these things as individual excitations in potentially kind of a large scale entangled quantum system. So there's a lot of things we still need to figure out, but this kind of maps out what I'm interested in and things that we've been pursuing in my lab to try to lay out some of the foundations for an interlayer exciton based quantum simulator. So finally, I should just really thank everybody that's been involved in the work. The first project on the interlayer tryons is primarily headed by Erfu Lui. He's a postdoc that Professor Joshua Lui and I share as advisors. And then the second part, this newer work, is basically written by Fatima and Trevor, who are now off doing better things than what's going on in my lab. But there are a lot of other people involved, and I think we will continue to kind of push in this direction in 2D materials while we're not doing other things in quantum biology and other topics. And lastly, my shameless plug, we do have lots of postdoc positions available. If you're interested to coming to Southern California, you can always reach out to me. We have a large effort using nanophotonic techniques in biology. And so we have some work that's going to be coming out very soon. But we do also still work in these 2D materials. And at Riverside, we have quite a group of people working together on photonics, but also electronics and transport in 2D materials. And just to entice any of you who aren't from Southern California, here's a photograph from a hill above my house. I live out in the mountains. It's a beautiful place. And hopefully I can entice some excellent students to reach out and think about coming to Southern California. So with that, thank you very much.
Great, thank you very much, Nathaniel. This very clear talk. So any questions? Otherwise, I'll just start. If you could just recap, what was the temperature again, where you saw these very, very narrow lines?
So in the first section, so this was at 5K at 0 field. So these were basically at 5 Kelvin. These lines persist up to about 20 or so Kelvin. You can see them. They start to be more difficult to resolve above 20 or 30 Kelvin.
And their lifetime broadened, are they?
We assume so. Yeah, we assume that they basically broaden very quickly. And it's also the challenge with these tryons is that they're much more weakly bound, presumably. And so, you know, at sufficient temperature, they become impossible to resolve. And this is getting improved with device quality. We can see them persist at slightly higher temperatures, but they still seem to be pretty sensitive to temperature.
And this funky noise that you see there, is that similar to what we heard about yesterday, this quantum detection?
It could be. Absolutely, it could be. And this has to do, this could have actually something to do with the localization. So as you go from, say, let's assume you have multiple tryons in a single track, you could see some unusual characteristics as those essentially relax, and you hopefully get to one exciton or tryon per track. And so some of those interesting effects, I think, are appearing in this data, and we don't fully understand them yet. Yeah.
Thanks for the beautiful talk. I have a very technical question. So these twisted structures on these semiconductors, what are the critical angles, or what, I don't know, what is the range of angles, and are they difficult to obtain, and what is the yield to have a very good sample?
Yeah. This is a good question. So we're unfortunately, I would say, in the business of kind of onesies and twosies, but we're able to do it kind of systematically. In this material, the first part of the talk, the angle is 0. We basically selected for angles very near 0. The way that we do that is basically you can essentially measure the device and then go back afterwards and use things like second harmonic generation to look at the relative angle. But we do get high yield. I mean, we were able to measure something now up to now, probably about 12 or 13 of these devices, the first set. And in the second set, the photocurrent measurements, we have 4 or 5 of the devices. So it's become routine, but I wouldn't say scalable. It's actually quite difficult. And one of the things that we find when we're doing them at this scale is that we can measure the relative twist angles kind of after the fact. And so we process the device, we measure it, and then we try to assess what those twist angles are. We don't have yet a huge amount of control where we can kind of select very specific devices. And nor do we have an army of students who are just, you know, like a factory producing these twisted samples. So we take what we get, and then we kind of very, very carefully analyze what those angles are.
Great. Okay. Thanks very much. And also
Yeah.
for staying in the time. So I think we'll move on. Thanks again.
Yeah, thank you.
Okay. And we'll come to the final talk of the session, which is in person again. Speakers, Olga Medveda, Moscow.
Mhm.
And if there's any issues, please just interrupt
No,
us.
I haven't.
Hey. All right.
Thanks.
Okay.
Good evening. My today's speech is about tunable photonic resonances in molybdenum trioxide flake. The trend to miniaturization of electronic devices make it especially interesting to study objects that allow to control light at the nanoscale. Natural backs of van der Waals crystal slabs of molybdenum trioxide is such of unique object with interesting properties. It supports long-lived infrared Phonon Polarityns with a hyperbolic dispersion, being very appealing for identification of fingerprints of organic molecules and strong coupling. The main aims of our work is to create the method how we can change wavelengths of these polarityns and its propagation direction. As previous speakers mentioned, molybdenum trioxide supports Phonon Polarityns. It's coupled oscillations of electromagnetic field and atomic grating. These biaxial crystals, the dielectric functions of these crystals, of these materials, is a tensor with different components along x, y, and z axis. These functions have strong phonon resonance, phone resonance, and it leads to formation of frequency range, so-called Strahlen bands, in which the waves from point source on the surface can propagate with hyperbolic or elliptical dispersion law, depending on the sign of in-plane component of the electric tensor. In this work, we are interested in both hyperbolic and elliptical regimes in order to demonstrate properties of these materials. Let's consider thin film of this material. If we take thin film, it will be an infinite number of modes. In this picture, you see three first mode, dispersion of these modes, and here we see distribution of out-of-plane component of electric field for fixed frequency. For our more interesting M0 and M1 mode because of their propagation distance along surface. Mentioned that effective mode index is quite large, and it helps us to reduce the wavelengths in crystal compared with the wavelengths in free space. On the other hand, if we put our flake on metal slab, the mode will change. It's because the metal has a mirror effect and the thickness of the flake effectively will double. It's because of it, for example, M1 mode will too much longer than the same mode in the area above air. Also, because of boundary condition on metal surface, in this system, only odd mode will propagate. Mentioned that the main aim of our work is to demonstrate how such modes can be excited and controlled. As clearly seen from these isofrequency curves, the wavelength vector is depend on propagation direction in the slab. So that we had an idea to create resonators in which a resonant frequency will depend on resonator orientation. Unfortunately, we tried many times to do nanostructuring, but these materials is difficult to structure, it degrades. We use different approach achieved by nanostructuring the media above flake. To do this, we put our flake on the metal grating. As I have shown in the previous slides, the effective mode indexes in the area above air gap and in the area above metal grating are different, and it may lead to the formation of resonant effects in these areas. And in the experimental FTIR spectrum, we really observe the sets of resonances in both ranges. It confirms our hypothesis about formation of resonances, but we need to do detailed analysis for correct interpretation of regions of these resonances. We assume that waves back reflected from the boundaries between areas above air and areas above metal, and so that we can write phase matching conditions in which n is the number of full waves in each resonator. This color plot shows reflection as a function of frequency and inverse ribbon width. If we add on this color plot the phase matching conditions as a set of dispersion curves with integer number n, we see that the maximum of reflection matched with these dispersion curves. Let's now see the experimental spectrum for fixed ribbon width. And if we mark this width on the color plot as a horizontal line and see in the intersection points between this line and dispersion curves, we see that its position matched with the position of resonances in spectrum. It means that we actually have Fabry-Perot resonances. Also, we can illustrate our resonances in distribution of out-of-plane component of electric field at the height 10 nanometers above the flake. If we will change frequency, we see that order of resonances also will change, both for metal grating and air gaps. In this picture, we see a distribution for 1A6M resonance in the spectrum is this one. To better corroborate our theory, we perform a near-field measurements. In these SNO measurements, Polarityns was excited by plane wave polarized perpendicular to ribbons and perpendicular to tip axis. And after that, not exciting the tip. After that, tip was excited with polarization parallel to tip axis. And this method helps us to directly demonstrate oscillations in flake. Also, in these measurements, we change angle between metal grating and main optical axis of flake. Let's consider more carefully this twist. Now we will consider the dependence of resonant frequency and rotation angle. In this color plot shows the reflection as a function of frequency and the rotation angle. We see that frequency change with rotation angle, and it's corroborated in the experiment. So that we had a clear dependence between rotation angle and resonant frequency. It was seen the first time. It wasn't demonstrated before. Also, we want to demonstrate how we can reconstruct dispersion surfaces in the experiment. If we construct dependence of two-dimensional wave vector on frequency in the hyperbolic range, it will be hyperboloid. Now we will mark on this hyperboloid resonant frequencies from previous slide. Now we want to dissect our hyperboloid by constant momentum surface, by cylinder. In the real space, this cylinder corresponds to using the same grating for all twists. If we go around this cylinder, we change angle between a metal grating and flake, we do twists. And if we look at the intersection points between cylinder and the isofrequency curve, we see that if it gives us the angles for which we see these resonances in the experiment. Also, we want to dissect our hyperboloid in different way by constant frequency points. In order to do this, we made a set of gratings with different ribbon widths and put our flake on them at such angle in order to achieve the same resonant frequency for all. And we mark these points on the hyperboloid and see that it fit well our analytical isofrequency curves. It leads me to the end. To summarize, we demonstrate in this work the measurements of polaritynic resonances in both near and far field. We developed a new technique of tunability of resonant frequency in resonators on the base of biaxial crystals by simple rotation. We illustrate how dispersion surfaces can be reconstructed experimentally, and our approach gives excellent opportunities to creation of tunable sensors, photodetectors, and strong coupling achievements. This work was done with a cooperation with colleagues from Oviedo University, Anna, Javier, and Pablo. Our MMPT group, Roman, Valentin, and Kirill, he is now working with Alexei in the IPC. Thanks for your attention. I'm ready to answer your questions.
Great, thank you very much. Thank you for sticking with the time. Any questions here?
So just very short question. Why don't you observe the M0 mode in the elliptical range?
Thanks for your question. Really, in elliptical range, we has only M1 mode because of for M0 mode, the effective thickness is 0 because of there aren't any oscillations in the Z direction. And for elliptical range, we have both the electric function along X and Y axis positive and no polarityns. In contrast, in hyperbolic range, we have different signs of the electric function and we have M0 mode.
Okay, thank you.
Thank you.
Okay, thank you. Any questions online in the audience? Shout it out or put it in, no? Put it in the chat. No, anyone else here? Otherwise it gives us our coffee break. All right, okay. So thank you very much then. And we'll close the session. And we've made up the lost time, so we'll reconvene at 5:25. Thank you.
Hi, just 1 second. Yeah. I want to...
Okay, so welcome everyone back. We'll have now the last session from today with 3 talks. The first one will be given by Alexander Bloch about quantifying femtosecond nanometer diffusion of hot carriers. So Alexander, when you want, the floor is yours.
Okay, thanks a lot. I'm very happy to be here. So let me just start by thanking all the people involved in this work, in particular work that was done in my PhD in the group of Nick van Hulst, and now I'm a postdoc here in the group of Klaas-Jan Thielroy at ICN2. So to start, and hello to everyone online, I want you to imagine you're in the Pyrenees on a camping trip. You just woke up. What's the first thing you do as a scientist? Of course, you get out your Bunsen burner and you make your coffee, right? So what happens is the Bunsen burner focuses to a small spot on your metal, and then the heat spreads, right? So what does this process, it's on a centimeter scale and it takes seconds, right, to heat up. And in fact, this heat is diffusing with roughly 1 centimeter squared per second. So this is the diffusivity of heat in metal. And this was actually known for a while, so early in the 19th century already. Fourier and Fick, they came up with this diffusion law, where the temperature is changing with this gradient squared of the temperature. So you have a hot and a cold thing, and you get this diffusive behavior, and it's quantified usually by the mean square width going up linearly in time, and this proportionality is the diffusivity D. So this is quite microscopic. So if we dive into the atoms, we can think of, well, there's probably particles, maybe it's electrons or phonons bouncing around in my rod. And this is actually the nanometric picture to explain this centimeter scale heat transfer, right? Okay, so let's, so what is basically the assumption here? The assumption is that the size I'm looking at, my rod, is much bigger than the mean free path of those scattering particles in my box, and also that the rate of change is much slower than the scattering rate of these particles. And that's when we get our 1 centimeter squared per second. But nowadays, we're going to nanometer size, right? Our computer chips are getting smaller and smaller. The modulation speeds are getting higher and higher. So basically, we are breaking this local thermal equilibrium. And if you look into it, you will find that the particles you're looking at are electrons and phonons, and they couple. So they are not anymore necessarily in a thermal equilibrium. So the question becomes, on the nanometer scale, can we translate diffusivity to 0.1 nanometer squared per femtosecond? So if you look very fast and very small, is the thermal transport still the same? And the answer, I will already take it away, no, it's very different. So you get actually hot electron diffusion, which is uncoupled from phonons and goes 100 times faster. So how can we really see this? So the idea is, I think, very easy. You know, the coffee cup, you just have a small spot and you look at the spread. But how do we do this? We need three things, I think, the holy trinity, which is temporal resolution. So we do pump probe. We need spatial resolution. So we do it somehow in a high NA objective. And we need sensitivity, which is usually some sort of lock-in technique. And you also want your signal to actually be proportional to what you're looking at. So one way to do this is what we call ultra-fast scanning transient absorption microscopy. So you take your pump, you focus it down as tight as you can to a submicron spot, and then you have your probe. And instead of doing pump probe where they are collinear, you can actually scan your probe over your pump. And so as a function of time delay, you can see that your initial narrow profile can really turn into a widened profile as you look at different time delays, and you're spatially mapping out this width. And the observable here is the transient reflection, so reflectivity. This was set up here in my PhD. You can see on a quite big table. We've now repeated in classes group the same setup on a 60 by 60 centimeter breadboard. So you can build this quite compact. This was done by Jake in our group, and all the hardware is interfaced with Python nowadays, and everything basically from scratch. This we didn't invent this technique. This was pioneered by a lot of scientists, mainly in the US, who've been doing this for, let's say, around 10 years. So what are the numbers here? I said temporal resolution. This is just the laser. So we take 100 femtosecond laser. The cross correlation is in the 200 femtoseconds. Kind of makes sense. You can also repeat the same experiments with tens of femtosecond lasers. So that comes for free, let's say. You just have to get the right laser. What about spatial resolution? This is a bit more subtle because we're doing far field diffraction limited optics. So we have our diffraction limited spot, but actually we're looking at the change in the width. So how much change of a 1 micron spot can you see? 1.1 micron? Yes, no problem. 1.01 micron? Maybe. So this is in the end limited not by the diffraction limit, but by the signal to noise of your Gaussian. So this is super resolution. And we quantified it here to say we're better than 20 nanometers in width precision, which I think if you do scanning near field, you say, ah, that's kind of good, but it's without a near field scanning technique. And then in terms of sensitivity, yeah, we basically try to get rid of most of the noise in our system and then roughly at 100 milliseconds integration time, we can get like 10 to the minus 6 relative signal. So we have the Holy Trinity. So what can we measure? Transport, of course, right? That's what this is all about. So what is transport? According to Wikipedia, it encompasses all agents of physical change in the universe. So this was good news. We can measure everything. So let me be a bit more concrete. What moves on the nanometer femtosecond scale? Let's say in physics, mass, energy, charge, heat, spin. So all of these transport things can be measured in such a way in space and time with high sensitivity. What I will talk about today very quickly is something on semiconductors, both bulky and two-dimensional. Then I will come to metal, maybe an old topic for people who are not doing classic plasmonics anymore. And then finally, the real 2D world with the graphene. So let me start with the semiconductors. So here, what we're visualizing is the exciton diffusion. And I'm going to go for silicon and MOSE2. So an exciton, I don't have to introduce, but what's interesting is here, when we shine with our pump laser, we assume that the profile we're creating is the exciton density profile. So this profile here, and that's the thing that we're tracking with diffusion. So this is the equation. You just have a diffusive term, here this nabla squared, and then you also have a decay exponentially, which is the exciton lifetime. And then again, we're looking at squared width over time. So I'm going to plot squared width over time, and the slope will be my diffusivity, right? Okay, so let's take a wafer. We do the collinear experiment. We have our pump and our probe overlapped, and we just scan the time delay, normal transient absorption. We get a decay, and then we start scanning our probe beam. And for different probe beam positions, we make this map, this spatial temporal map, so probe beam position versus pump probe delay. And the information about the diffusion is here in these Gaussian profiles. So we fit a Gaussian at each time delay, and then we look at its width evolution. So full width half max over time squared is then a linear slope, and the slope is the diffusivity. So we get here 11 centimeters squared per second. Then we can do the same thing with MOSE2 flakes. So we have monolayer semiconductors, and we see basically roughly the same thing. The exponential decay is different. It's a different time scale. We get a different spatial temporal map, but full width squared over time actually, in this case, for this mobility, happen to be roughly the same number. So we get 12 centimeters squared per second, very much in line with what was previously reported in the literature. So this, I would say, benchmarked our setup. So we never even published these results, although now we have a thickness-dependent study also going on. So let me go to gold. So yeah, as I said, an old material, but now what we're looking at is not anymore the excitons, of course, but it's the hot electron temperature distribution. So how is this understood? So if you absorb light in gold, you get a very much non-equilibrium situation. Let's say in the first femtosecond, you create carriers here. And what happens in 10 to 100 femtoseconds, you get a thermalization. So your electron gas actually goes up in temperature, much higher than the lattice temperature. And then let's say hundreds of picoseconds later, you will be in this regime where your electron and your lattice are at the same temperature. So this is called the two-temperature model. And the reason that the electron temperature can really go so high, up to 1000 Kelvin, is basically that the electron system is characterized by its own heat capacity, which is 100 times lower than the lattice heat capacity. So now the question became, this is all well known, but actually how do we get from here to here? So what is happening from the hot electron to the thermalized regime? Mainly people will answer probably electron phonon coupling. Yes, that's right. But there's also the hot electron diffusion. So spatially, the hot electrons can actually diffuse out of plane. But this in a purely temporal study cannot really be disentangled. So the idea is here, these non-equilibrium electrons and phonons, can we now look at them in space and time? And the idea is that you have your initial Gaussian, and the hot electron diffusion will make it spread laterally, while the electron phonon coupling will just make the Gaussian decrease. So in this way, we can disentangle these two phenomena just by doing spatial temporal. So how do we image this? Same as for what I showed you before. We do our time traces. We actually get two decays here, one on a single digit picosecond, fast part, and then a slow part over hundreds of picoseconds. And so we take our slices of our spatial temporal scanning at the different time delays. And again, we cut them open and we get our spatial temporal profile. We look at the full width half max, and wow, this looks different. So now we have a linear slope in the beginning, a linear slope in the end, but very different numbers. So we get our 1.1 centimeter squared per second, which is the coffee cup regime. But we also have this very fast spread, 100 times faster in the very beginning. And actually, if you just think about it, it actually comes back to these heat capacities. So the electron system, when it's not coupled yet to the phonons, it has this higher hot electron diffusivity, basically just because its heat capacity is 100 times lower. So this was sort of known, but also a bit forgotten and never really measured in the literature. So we get this 100-fold higher hot electron diffusion that I was talking about in the beginning. Yeah, so this transition from fast to slow, it can really be understood also in terms of simulation. So we use the 3D two-temperature model, which is just this equation here, which has for the electron and the lattice heat, a similar equation like what I showed you for the silicon. So you have a diffusive term, and you have then this decay term, which is now coupling these two differential equations. So then we calculate our electron and our lattice heat profiles. Then we convert it here into a permittivity with a thermo-optic model. Then we convert this into our observable, which is actually transient reflection with Fresnel equations. And then in the end, we get our simulated spatial temporal profile, and we can do our Gaussian fitting. So we get here these 1000 kelvins, like always in the two-temperature model. The lattice temperature just rises slowly within 5 picoseconds. But most importantly here, the width over time does exactly what I told you before. The solid curves are now our simulations. So for the different fluences, it all kind of seems to make sense. So this is pretty much well described. So this is a very quick side note. So in fact, there's something kind of subtle in here, which we didn't go into much detail in this paper, which is if you exclude the electron phonon coupling, okay, the width spreads, but if you then turn it on in the simulation, you see that the electron temperature shrinks. So here we go from 0.3 to 5 picosecond, it spreads, and then from 5 to 10, there's a slight shrinking in there. So kind of again, this full width over time, it goes up. In the end, it goes to 1, but in the middle, it actually decreases a little bit, which we thought was kind of interesting, especially if you think of what is a negative heat diffusion. That's heat contracting. That's not allowed to do to thermodynamics or something like that. But in this two-temperature regime, this absolutely does make sense. And so actually, if you then convert the electron temperature, which does this decreasing of the width, into our observable, which is the transient reflection, you see it also kind of goes down, but the effect is quite smeared out compared to the pure electron temperature, which we're not measuring. We're measuring the observable delta R. So the conclusion is this shrinking exists, but we're kind of washing it out. And with our error bars here between experiment and simulation, you might say it's going down, or you might say we don't have enough resolution. Yeah, so this really gets smeared out when you go to our observable, but that doesn't mean that the effect is not real. With this, I'd like to come to the last part, which is graphene, finally a real two-dimensional material. And this time, the observable won't be the transient reflection. In fact, we're going to now to photocurrent. So first of all, graphene, of course, it has this very high mobility. So we expect a very high diffusivity, right? And actually, we can directly predict this Carrot diffusivity straight from this Einstein relation, which tells you how mobility scales with diffusivity with this very simple law. And because we have this Hall bar geometry, we can do normal transport measurements and get a momentum scattering time on the order of hundreds of femtoseconds. And we can get, for different Fermi levels, as we change the gating, predict this roughly 2000 centimeters squared per second in diffusivity. So let's measure it. So this is the idea. You have a split gate sample where you can independently control the gate voltages on the left and the right. And then you come in with your laser pulse. like in the gold, you get your diffusion out of plane. You do the same thing on the other side as well. And what we're actually looking at is how this hot electron diffuses to the split gate region, which is where the photocurrent gets created. Already known here in this nice paper by Natalia Gabor from 10 years ago already, very nicely explains where this photothermoelectric photocurrent comes from. And now the idea is by changing our pulse delay and also our spatial offset, we're again getting a spatial temporal information, because how this interacting heat manages to reach the split gate region will tell you how fast it diffused. So this is then the data set as a function of the spatial offset and this temporal offset. We get our photocurrent signal of the interacting heat at the junction. And right in the middle, it's narrow. And then if you go towards the sides, it's broader. So it's again this diffusion, right? And now this is the data for 3 different Fermi energies. So we're making our split gate by putting negative voltage on one side, positive on the other, the PN junction. And so by tuning this, we can control the Fermi energy. And the spatial width over time looks like this. It kind of spreads. So what we put in here is actually the diffusivities of our electrical measurement with the Einstein relation. So in some sense, this simulation, this calculation here and the data predict very well this diffusivity of 2000 centimeters squared per second, which is already faster than the hot electrons in gold. But I didn't exactly tell you the truth, because the focal spot sizes we measured very precisely, and we actually think these curves should start down here. So there's something going on. There's something which we call a Fermi level dependent initial broadening. So within your instrument response time of hundreds of femtoseconds, you already got a very big spread right there in the beginning. So where could this come from? And this is actually explained in the hydrodynamic regime of transport. So very quickly, diffusive regime just means electrons are bouncing off phonons, impurities and whatnot, but not feeling each other much. There's no strong electron-electron interaction. But when you reach the hydrodynamic regime, in fact, the electrons feel more each other than the defects, and you get viscous flow. So this was shown mainly in terms of geometry scales engineering in the last couple of years, where you try to get your electron-electron interaction length the smallest scale of the system, and also your sample shorter than the momentum scattering time. So this I call length scale engineering. What we do is slightly different. And on top of this, we go to the so-called Dirac fluid regime, which is when you tune the electron temperature higher than the Fermi temperature, you actually get the coexistence of electrons and holes. So the transport is again, even on top of the hydrodynamic regime, altered. So for high electron compared to Fermi energy, you enter this quantum critical Dirac fluid regime. And what was observed in this regime is actually a violation of the Wiedemann-Franz law, which means our Einstein relation, our Wiedemann-Franz law, they don't hold anymore. Heat is now transported much more efficiently than charge. So we're going to again break the known laws. So the question is, can this Dirac fluid show an enhanced transport above room temperature? Because this was here at cryogenic temperatures and at very small carrier densities. But now we play this trick of going to high carrier temperatures, and then we can do it at intermediate densities. So now we do this timescales engineering. So it's not geometric engineering. We have our infinitely big sample, but we do that we find that our timing is important. So we're now looking at times faster than the momentum scattering just by using our ultra-fast lasers. And then we have our 2 knobs of the laser power and the gate voltage to control continuously electron temperature and Fermi level or Fermi temperature. So now all these combinations of a P and N junction and P junction, you can do this trick of putting high power but a low Fermi level here in the middle, or low power and high Fermi level to tune in and out of this Dirac fluid regime. And in fact, you see for this combination of electron temperature higher than Fermi temperature, a larger times 0 width. So we're trying to kind of understand this initial broadening here, right at time 0, and we see that it scales with these tuning knobs. So if we do it for a whole range of electron and Fermi temperatures, again by tuning power and voltage, you see that you really get this classical V shape of the Dirac fluid regime. So we performed with our collaborators, Alessandro Principi in Manchester, these calculations. And you can really see how the diffusivity goes from the known value of 2000 centimeters squared per second up to over 10 to the 5. So another factor 100 faster diffusivity in this Dirac fluid regime for a sample that's already record high a thermal conductor. And the cool thing here that you can really control this continuously with your knobs of a voltage and your laser power. So if I go back to this slide I showed you earlier, you can really now kind of understand this initial offset as a diffusivity with a very high number, 10 to the 5 centimeters squared per second, which only lasts for the hydrodynamic window before your momentum scattering kicks in. And this is now basically how we understand this, and the numbers are quite impressive. So you have many tens of thousands of centimeters squared per second. Remember the coffee mug, it was 1. And if you then translate this to thermal conductivity, you even get a factor still 10 higher than the phononic contribution for graphene, which is higher than diamond and record high. And this is although you're in the regime of this low heat capacity of the electron system. Yeah, so very much higher than phononic thermal conductivity we find, and we think this is really important then for heat management because yeah, you can really transport away heat much faster than let's say by classical limits was expected. Okay, with this I already want to summarize what I told you. So on the one hand, I showed you a kind of benchmark of our purely all optical spatial temporal microscopy with this idea of scanning a pump over a probe and looking at, let's say, semiconductors and it seemed to make sense. Then we used the same technique to look at hot electrons in gold and really due to this 2-temperature model could understand this fast diffusion in the beginning of 100-fold enhanced in the first picoseconds. And then finally, I went to graphene, and with this thermoelectric microscopy, we were able to show that, yeah, you can really tune in and out of this, not just hydrodynamic, but Dirac fluid regime with these very high thermal diffusivities and translating to conductivities. So this really means after you illuminated your sample, what happened spatially was a much faster than even ballistic transport due to this hydrodynamic regime of electrons and holes kind of acting in unison. And with this, I'd like to thank you for your attention.
Thank you, Alexander, for the very nice and clear talk. So are there any questions from the audience?
Thank you, great talk. So how do you actually localize spatially the spot? Because you said that you're on a scale of 50 nanometers. So if your pump is at 400, you should get around, well, twice smaller, 200 or something.
Yeah, so in the gold experiments, we focus 400 nanometer light with 0.6 NA objective or something. So the spots are not tiny. The spots are around just below a micron. But the idea is to then see the spreading from 1 micron to 1.1 micron, if you know what I mean. So we're not tiny spots, but we're able to resolve very small differences.
Okay. And which laser do you use?
The gold experiment was the TISAF 400 and 800, or actually 450 and 900, I think. And then for the graphene, we used red, so we didn't want to use our blue anymore. So we did identical TISAF lines, 880 nanometers.
I see. And one last question. So when you compared the measurement on bulk, was it silicon?
Yeah.
And molybdenum
yes.
oxide, yeah? So what was the substrate for molybdenum?
The molybdenum on glass.
On glass, okay, thank you.
Yeah, and actually the fact that the two numbers are so similar is a bit of a coincidence, because in this case of silicon, it just happened to be the doping of the wafer that we bought that made this number match to about 12 centimeters squared per second. Yeah, and the molybdenum was on glass.
Okay, so any other questions from the audience or from the chat? Okay, so let's move to the next talk, which will be given by Jiahua Duan from Oviedo. Yeah, and the title of the talk is Twisted Nano-Optics, Optical Topological Transitions. So go on whenever you want.
Good afternoon, guys. So I'm really honored to be here to share you with our recent work, and also thank you, Alexei, invite me to give me this opportunity. And my name is Jiahua Duan, and I'm coming from University of Oviedo. Today, in my presentation, I will give you some demonstration that how can we visualize optical topological transition, and how can we do something with this topological transition. So in these three images, I just want to give you a brief impression that how different the wavefront can be in different media. So if we just imagine if we in isotropic media, if we we throw a stone into water, and then we will have this wavefront of the wave as the circular one. But as Pablo just gave a presentation about the anisotropic media, when we transfer into that, we have this concave wavefront, which is quite counterintuitive. And also in another system, you can see we have this quite strange or exotic, highly guided propagation of the wave. So we can call it a twisted system. I will explain you later about the detail, how can we realize this thing, and why it is important for us. So just in case I don't have enough time, in the end, I want to give my acknowledgement to our group and also our collaborators. We are a small group in Oviedo, and headed by Dr. Pablo Alonso Gonzalez. And we are always open to collaborations. If you have some interest in our group, please just scan this QR code. You can have our website. And at the same time, I want to thank you, our collaborators, especially Alexei Nikitin from DIPC, and also Valentin Volkov and Kirill from the MIPT, and Nathaniel for their theoretical support, and also Ivan from Austria for the fabrication of samples. So I will skip this introduction just to give a brief introduction, because I think you are all experts in this community, and also Pablo gave a quite clear demonstration of the introduction. So we all know that polarityns is a half light, half matter particles. It is quite important for us because it can provide us a solution to confine light into a nanoscale for no matter the mid-infrared or terahertz. So I borrowed this image from Andrew's poster because I like it a lot. It's just we can couple the photon to phonon, and then we will have some strong coupling, and then we have this half light, half matter quasi-particle. We can call it Phonon Polarityns. So this is one specific type of the polarityns. So it's like we illuminate the polar dielectric, and then we can have this strong coupling between light and the lattice vibration. If we want to observe or study these polarityns, we need to use this well-known technique. We can call it wavefront mapping. It is quite famous. You can imagine we put a gold antenna on top of the on top of the sample, and then we illuminate the antenna with some instant beam, and it will help us to efficiently launch the phonon polarityns. And then we use the AFM tip here, raster scan the sample. Simultaneously, we can have probe the near field amplitude and phase information. And with this technique, there are a lot of the groups working on the phonon polarityns, such like in 2014, Bessel's group in Columbia University, they find this phonon polarityns in boron nitride, which is one representative van Waals crystals. And also our group collaborating with other groups, so we find other phonon polarityns in other materials, such as this one, molybdenum trioxide, and also this one, vanadium pentoxide. So in this talk, I will focus our attention on molybdenum trioxide. I will explain you later why this materials is interesting for us. So here I gave you some representative materials now scientists are quite interested in. in this Polaritonic community. So we can character them by different different crystal structures, such as with the boron nitride, we can have these hexagonal crystal structures, and because these crystal structures, we can have this tensor of the permittivity. If you notice, you can see along X and Y direction, that means the in-plane components of the permittivity is exactly the same. But out of plane, like epsilon Z, that is not, it's completely different, no matter, not only for the value, but also for the opposite sign. So that means in boron nitride is the in-plane isotropic medium, but out of plane hyperbolic medium. And in this row, I just show you the isofrequency curve, but in this slide, you do not need to pay much attention. I will explain you later why this is important, but you just need to notice how different can be in the different materials. So since it can be different in molybdenum trioxide here, we can see along the in-plane component, like along X direction and Y direction, it can be completely different with the opposite signs and different values. So that means even online in plane, the molybdenum trioxide is a hyperbolic medium. So these two materials are all of them are the van der Waals crystals, such as like 10 years ago, we moved our interest into the van der Waals crystals because van der Waals crystals can provide us a high field confinement, and also we can quite easy to structure the materials. But now it looks at some of us turn back to the bulk materials because of the low symmetry. We can see like low symmetry materials provide new hopes for the infrared nanophotonics because they can support some quite exotic Phonon Polarityns modes. Because here I can show you two representative example in calcite. This one because it is also uniaxial materials, but because it is bulk materials, we can exfoliate like along different interfaces. So that means we can guarantee that the optical axis is slanted with respect with the interface. So it will provide us some quite exotic strange things like both the volume and the surface confined Phonon Polarityns. And also another one is gallium trioxide because it is the monoclinic, and we can see in its tensor of the permittivity, we cannot even diagnose this permittivity. So we have this, they will have this undiagnosed component and provide us more degree of freedom for the Polarityns. So today in my presentation, I will focus on the molybdenum trioxide and show you how can we do more things with these interesting materials. In order to understand more about these Phonon Polarityns, we need to get very clear about one definition. We can call it isofrequency contour. It is the dispersion surface in the momentum space of a constant frequency. We can see here it's completely different in boron nitride and molybdenum trioxide. In boron nitride, in 3-dimensional, we have this one, the open hyperbola. But if we make an in-plane cross section here, we can find it is a circle. So that means it is the in-plane isotropic medium, and then the pointing vector is always collinear with the wave vector. And along every direction here, we have the same magnitude of the wave vector. Correspondingly, in real space, we will have this just as I showed you before in the first slide, we will have this circular wavefront propagation. But things can be different in molybdenum trioxide. If we make a in-plane cross section here, we can have this open hyperbola as the isofrequency curve. So that means the pointing vector and the wave vector is no longer collinear with each other, and along different directions, this k can be dramatically changed. And also along this direction, you can see we will not have the solution for k. So correspondingly, we will have this concave wavefront in real space. We can call this one in-plane hyperbolicity, and this will give us a lot of the interesting phenomena. As in Pablo's talk, he already gave like anomalous refraction based on this in-plane hyperbolicity and also the focusing. If you are interested, also you can read these two papers. So here in the following slides, I want to show you how can we do more with this in-plane hyperbolicity. We were quite inspired by this beautiful work published in 2019 by Pablo Haril in MIT. They find this magic angle graphene. They find if they twist the two bilayer graphene at a critical angle, they will find this. They will have this flat band in the electronic band structure. And then they found a lot of the interesting phenomena like superconductivity and so on. So we were quite inspired by this work because we were thinking, what will happen if we bring this concept of the twist into our optic realm? So please remember, we cannot do this one before the molybdenum trioxide, because you can imagine in an in-plane isotropic medium, we always have two circles as the isofrequency curve. No matter we rotate them, it will be always the same. But now with the molybdenum trioxide, we have these two sets of the open hyperbola as the isofrequency curve. Just imagine if we take into account the electromagnetic coupling between two layers, and then we put them together and we rotate them with the different angles, maybe we can find something interesting. In order to answer this question, we conduct some theoretical calculation at the first stage. We put two slabs of the molybdenum trioxide together, and we put a dipole in the simulation to launch the Phonon Polarityns inside. We find that when the twist angle is like 0 degrees here, it's more or less like the case of we find in the monolayer of the molybdenum trioxide. It's in the real space, it's a concave wavefront, and correspondingly in K-space, we have this open hyperbola as the isofrequency curve. But things can change if we increase the twist angle to 90 degrees, as here. We find in real space the wavefront becomes closed, and we will have the wave propagation along every direction. That means we will have this closed isofrequency curve in the K-space. That means we can change from an open hyperbola to a closed isofrequency curve. This we can call it optical topological transition. But we were thinking, what will happen at exactly this transition? So we find this thing. If we twist the bilayer of the molybdenum trioxide at a critical angle, like 63 degrees, we find the isofrequency curve becomes completely flat in the K-space. What is interesting about that one? You can imagine if the isofrequency curve is completely flat and all pointing vector only can point along one direction. That means in the real space, the wave can only propagate along one direction. We can call it highly guided, or we can also call it canalization of the Phonon Polarityns. So in order to realize it experimentally, we design these measurements. We put the two layers of the molybdenum trioxide together, and we put a gold antenna, and we use the technique I showed you before, and we measure the near field amplitude signal. So we find if the twist angle is 0 degrees, it's more or less like the case in the monolayer of the molybdenum trioxide. We have this concave wavefront. But if we increase the twist angle to 30 degrees, we still find this concave wavefront, but it is tilted a bit compared with this one. So correspondingly in K-space, we have still have this open hyperbola as the isofrequency curve, but it is tilted a bit. And if we further increase the twist angle to 90 degrees, we find this closed wavefront in the real space fits quite well with our numerical simulation I showed you before. And we in the K-space, we have this closed isofrequency curve. So that means exactly we can observe this topological transition from open hyperbola to closed one in the measurements. And more importantly, we want to exactly realize this flat band as the isofrequency curve in the measurements, near field measurements. So we find if we fix the twist angle around like 54 degrees, we find, yes, exactly, looks quite flat in the K space, and all pointing vector can only point along this direction. That means in the real space, when it goes to antenna launching the phonon polarityns, it can only propagate along this direction. So we can call this one as the canalization of phonon polarityns. Why it is so important for us? Because I can show you in this slide. So if we enter into the canalization regime, you can imagine if the pointing vector only points along one specific direction, we will not have the diffraction of the polarityns. So that means we will have this diffraction-free or low-loss propagation. In order to verify that thing, we extract the line profile from the experiments from the canalized phonon polarityns and also common hyperbolic propagation of the phonon polarityns, like here and here. We use this equation to fit this experimental result. And if you notice, the F here is the factor to determine the geometrical decay. So we can find here in the canalization regime, the F equals to 0, compared with the case F equals to 0.5 in the hyperbolic propagation. So that means there is no geometrical decay of the for canalized phonon polarityns. This is quite important for us to have a low loss and highly guided propagation of the mid-infrared light energy at the nanoscale. So we published this paper in Nano Letters. If you want to read more details, you can reach to this paper. And also there are other 3 papers published at the same time with the similar concept. You can see this topic is becomes quite hot now. And as in Frank Koppen's perspective in Nano Letters, he called this one is the rise of the twist optics. I can understand because we can call it twist optics because we prove that here the photonic energy band is quite sensitive to the twist angle between 2 layers of the molybdenum trioxide. And in the previous slides, I show you that what can we do with the bilayer, twisted bilayer molybdenum trioxide here. We can observe this topological transition from a closed one to open hyperbola, and between them we have this flat band isofrequency curve. But in the monolayer, only monolayer of the molybdenum trioxide, we developed this equation to analytically calculate the dispersion of the phonon polarityns. And we can have this in monolayer of molybdenum trioxide, we have this open hyperbola. If you notice that there are in this region, the red shaded region, we don't have the solution of the for the wave vector because it's an open hyperbola here. So we were thinking, can we enter into this forbidden direction? So as a physicist, we want to do something impossible. So we want to find some solutions in this equation. If you notice this equation, you will find that the dispersion of the phonon polarityns depend on these 2 parameters, epsilon 1, epsilon 3. This is the permittivity of the substrate and superstrate of the molybdenum trioxide. So in the common case, we always fulfill with this condition, like the real part of the permittivity 1, the epsilon 1 and plus epsilon 3 is always positive. This is quite easy to understand because we always use like air as the superstrate here. So the permittivity is the 1. And we always use the silicon dioxide as the dielectric substrate. So in this, when we fulfill this condition, we have the propagation centered along 1, 0, 0 direction, which is the crystal direction of the molybdenum trioxide, like here, I show you in a specific resonant band, of course. But we were thinking, what will happen if we break this condition? Like we enter into another condition, like the real space epsilon 1 plus epsilon 3 is negative. So in order to fulfill this condition, we need to carefully choose the substrate because we need to guarantee that the permittivity of the chosen substrate is negative and maybe more negative than -1 in the frequency we are interested in. So we can choose this 4H silicon carbide because it has a perfect permittivity for us. And here I can show you what will we observe if we do this thing. So we conduct some analytical calculation here. If we put a molybdenum trioxide on the silicon dioxide as a dielectric substrate, it is quite common, like what we observed before. We have this dispersion along 100 direction, but we don't have anything along 001 direction. So this means we can have this open hyperbola here. So it is quite easy to understand. And then in real space, we have the propagation centered along this direction, but there is no propagation along this direction. But things can be changed if we put the molybdenum trioxide on silicon carbide. Here, we find something quite interesting. Below the frequency of the surface optical phonon of the silicon carbide, we can change or move the dispersion of the Phonon Polarityns from 100 direction to the 001 direction. That means we can completely change or rotate the isofrequency curve like 90 degrees here. So in the real space, it will have something like this one. So we can have this propagation along this direction, centered along this direction. So that means that's told us by tailoring the dielectric environment of the molybdenum trioxide or Van der Waals crystals, not only we can change the wavelengths of the Phonon Polarityns, but also we can change the propagation, or we can change the isofrequency curve of the Phonon Polarityns here. So in order to realize this thing also in the measurements, we did some similar measurements with the snow. We put a gold antenna on molybdenum trioxide and we put them on silicon carbide here. So we compared with this is the near field image here. We compared it with the molybdenum trioxide on silicon dioxide here. And you can find at the same incident frequency, you can find this is a gold antenna here on silicon dioxide. We will have the hyperbolic propagation on concave wavefronts centered along this direction. But if we change it to silicon carbide, we will have some hyperbolic propagation or concave wavefront along this direction. And the measurements also fits quite well with the numerical simulations. Here we replace the gold antenna with a dipole, of course, in the numerical simulation. Okay, so, and we were also thinking what will happen between these two rotated the open hyperbola. So please remember, we observe this thing in a natural medium with a low loss. So in principle, we can observe this thing between these two states. So we observe this thing by changing the incident frequency. We find between this open hyperbola, two open hyperbola, we have this quite strange or exotic crossing linear as the isofrequency curve here. And we observe, that means we observe another type of the topological transition from open, gap opened, gap closed, and then gap open again, but we rotate it like 90 degrees. And this fits quite well also with the analytical calculation. I will use the last minute to highlight that this crossing linear of the isofrequency curve is quite exotic, even quite difficult to be realized in metamaterials. You can see there are some quite peculiar properties here, because if you have this crossing linear, you will have only along these two directions for the wave vector, and every point you will have the perpendicular S and the K. So that will give us more, maybe give us more opportunities for the polarities. That would be all I want to share with you today, and thank you for your attention. Any question would be highly welcome.
Thank you, Luan. Very nice results. So any question by the audience?
Hi, very nice results. I have a question, actually a curiosity. How sensitive are you on the angle? I mean, for magic angle graphene, for example, if you don't match 1.1, but you go at 1 degree, you lose the magic of magic angle. Here, if you, instead of before you go at 55, for example, you still get this nice result, or you destroy the magic?
Yeah, this is actually a very good question. So I need to explain a bit here because our physics behind this work is a bit different from the more physics in the magic angle of the graphene. So here we just the behind physics is just interlayer electromagnetic coupling, and the magic angle is not so sensitive to the like 0.1 degrees. It's more or less like 1 degrees or 2 degrees, and then you will remain in the magic angle. Thank you for the question.
What is the typical separation between the layers?
The typical separation. I think the typical separation is 0, but of course in the sample fabrication, maybe we cannot guarantee that there is no air layer between the layers. But in theory, and we didn't take into account the interlayer between two layers of molybdenum trioxide.
Okay, so I think we should move to the next talk because we are already like a couple of minutes behind the schedule. So let's thank Duan again. And the last talk will be an online talk given by Seebeck Coefficient. And the topic of the talk will be atomically thin electro-optic polarization modulator. So Seebeck, whenever you want.
Can you all see the slides and am I audible?
We can.
Okay. So I'd like to thank the organizers for giving this platform today to talk about some of our recent results. I'll be talking mainly about a platform that's atomically thin, and we'll be using that for electro-optic polarization conversion. I'd also like to thank the funding agencies for providing the money, and also the collaborators for a fantastic collaboration, and highlight our recent publication related to this work. So if we think about the properties of light and how to control them, we can break them down into some distinct qualities such as amplitude, phase, wave vector, and polarization. And to be fair, polarization is not really an independent property. It's rather a vectorial sum of amplitude and phase if you break them down in the x and y basis for a normal incident light on the xy plane. And if we just have a monochromatic assumption, we can see that we can tailor the properties of light just by controlling the amplitude, phase, and wave vector. And so traditionally, in most of the tabletop experiments in lab, we use a lot of bulky and passive elements that actually work great in tailoring these properties. So we have lenses, we have mirrors, we have wave plates, objectives, and they're supposed to do one particular function, and they do that function very well. But nowadays, there's been like this idea of kind of miniaturizing all these optical elements and making them reconfigurable. And what I mean by that is that you can change the properties of these elements by applying some external stimulus, and you can change the functionality. For example, you can change how much amplitude it spits out, how much phase it can give out, or what is the polarization state of light. And so this is a nice review paper in Science a few years back, where they showed all the different schemes that you can adopt, where you can have electrical doping, you can have photo generation of excitation, you can have phase change materials, you can change the surrounding environment like liquid crystals, and so on and so forth. So a natural question to ask is what has been done so far, and these are some results on the left by both our group at Caltech and also Professor Brungesma's group at Stanford, where we showed that by using a transparent conducting oxide, you can dope the system and change its doping concentration. And as a result, you can change the amplitude and phase of light, and you can create metasurfaces that can act like a spatial light modulator. You can create a lens out of it, and you can have other functionalities. So obviously now, as we explore more and more metasurface motifs and designs, there's also a hand-in-hand advancement in understanding some new material properties. And so on the right, if you see, these are some recent results from the Lipson group at Columbia and the Brungesma group at Stanford, where they showed that by using a transition metal dichalcogenide integrated in a waveguide, you can tune the properties of the waveguide transmission almost in a lossless fashion by operating very far away from the excitonic frequency. And at the same time, you can pattern a really large area of tungsten disulfide in a Fresnel zone plate, and you can spatially modulate the phase properties of light, and then you can generate what is basically a lens. And then by changing the electronic susceptibility of the layer, you can modulate the focusing efficiency of this device. So these examples kind of leverage new 2D materials, and in this case, semiconductors and their excitonic properties. And so in all of these examples that I showed, you can see that there's been a lot of emphasis on amplitude and phase of light electrically, and not so much about polarization. So a natural question arises is that can we think about polarization control of light, and what are the key factors that we need to address? So if you want some convincing why we care about polarization, I've listed a few examples. First of all, if you want to do imaging in neurons or fibers in brain that have some dichroic activity, you can get very nice information about depths or dichroic activities by doing Stokes imaging, or what is known as polarized imaging. And this is much more rich in information than just an intensity mapping. You can also do dichroism sensing in molecules, proteins, and biomaterials. In this case, this group explored domains of polarization boundaries in this insect or its wings, and they were able to do that by measuring the dichroism of the reflected light in the terahertz frequency. And of course, in terms of computing, you can have what is known as polarization encoding, where you encode your photon with a very specific polarization. And then you can do all sorts of things like entanglement. You can exchange information in a very secure fashion where third party cannot eavesdrop, or you kind of ruin or scramble your polarization in the process, and then your information is lost, and in a sense it's sort of secure. You can have also other functionalities like vortex beam generation, stress strain analysis of different polymers, and also you can have very interestingly resonant excitation into different cavity modes that are very polarization selective. So say, for example, you wanted to do a pump probe experiment where the pump is right-hand circular polarized and the probe is left-hand circular polarized, and you want to study the difference in dynamics. You can do that by using polarization conversion. So we're not the first ones to think about polarization conversion. A few years back, there was some back-to-back results from these three groups of Zayat, Brungesma, and Brenner, where they used different forms of metamaterials, and they made in this case, I'm highlighting one of them where they made basically a matrix and nanorods of gold. And then by carefully designing the excitation and the metamaterial in such a way that you have difference in the ordinary and extraordinary light, you can generate this difference in amplitude and phase, and you can have what they showed to be quite nice polarization conversion. So if we take the key ideas from these works and map it onto our goals, we want an active platform, ideally electrically, so that we can control the properties. And we want something that's naturally birefringent or nanostructures that break in-plane symmetry. But one problem of working with nanostructures is you kind of have them fixed at the fabrication time, and you don't leverage the natural birefringence or the birefringence tuning. So if we think about active platforms, we obviously have a large variety of possibilities, such as we have doped semiconductors, we have semi-metals like graphene, which operate through free carrier absorption and modulation. And we have had nice talks in this N2D with all the Plasmon Polarityns that leverage this idea. We obviously have semiconductors, which have band edge absorption, and the relatively new class of systems, which is 2D semiconductors with strong excitonic response. In terms of natural birefringence, if we think about the crystal structure driven response, we obviously have two kinds of birefringence that was discussed in the previous talk. You have in-plane birefringence, and then you have out-of-plane. And then you obviously have more bulky systems like liquid crystals and lithium niobate and barium titanate. But for today's talk, I'll focus on this particular material that has in-plane anisotropy, which is black phosphorus. So black phosphorus is an interesting 2D semiconductor quantum well, which has a puckered crystal structure. So imagine a sheet of graphene and basically displace or distort half of the atoms in the out-of-plane direction. And what you get is pretty much a black phosphorus unit cell. And so what this means is that it has now symmetry constraints which provide this large anisotropy, where if you look at the respective crystal axes, which is the armchair and zigzag respectively, you see a large difference in the optical activity. And then also if you map out the dipole emission pattern, you can see that it's a linear dipole with high visibility. And so that's very nice for our purposes. And the other interesting thing is that in black phosphorus, you have a very thickness tunable excitonic energy or band gap. And it's dictated by the fact that the exciton is at the gamma point of the band structure. And so you have this interlayer coupling changing the amount of, basically renormalizes your band gap, and you kind of see that manifested as a direct band gap all throughout in this layer dependent energy dispersion. And this is in quite contrast to TMDCs, which very quickly become an indirect band gap when you go from monolayer to bilayer or few layers. And the last property that we're going to leverage is the large electro-optic tuning, where we use different quantum well electro-optic effects like Pauli blocking and suppression of the band edge and Stark shifts to basically tune the transmission or reflection from black phosphorus. So now I'll get into the details of our work, how we conceptually thought about polarization conversion. So in this case, we chose 3 layers of black phosphorus, and this was mainly motivated by the need to work in the telecom frequencies or telecom wavelength bands. And we embedded this in a relatively low Q Fabry-Perot cavity with a back reflector of gold and a top reflector of well-chosen impedance-matched thin gold. And the idea is that we will have electrical contacts where we will be able to change the charge density in black phosphorus, and by that we can modulate the polarization state of the light. And so if we now represent this in the Poincare sphere, we can see that we have nice trajectories on the Poincare sphere where we see quarter wave plate and half wave plate like action. And this is basically saying that we can tune through these states, and then we can achieve different optical functionalities in our nanoscale device that we can do with bulky passive elements in the lab, all within the same device. So we began our characterization of 3-layer black phosphorus by using a field effect geometry, and we looked at absorption as a function of doping density. And so what we basically saw was that as we changed the doping density, we have a large tuning of absorption. In this case, we saw that the hole doping was more efficient, and we believe that it's more related to contact being much better in terms of hole injection rather than electron. But you can see nevertheless that we have a large tuning of the absorption. And when we back this out in terms of some optical constants, such as refractive index, we can see that the armchair has a large tuning of the real and the imaginary part of the refractive index, whereas the zigzag, which is the optically inactive axis, remains pretty much flat. And so such a large birefringence, if you see 1.5 is extremely high. If you compare that with like lithium niobate or other liquid crystals, you have something an order of magnitude, if not orders of magnitude lower. And so the reason why we think that this is the case is because we're basically having 2 predominant effects. One is the screening of the exciton, which is when you have more charges in the system, your exciton is being efficiently screened, and as a result, its binding energy decreases, your wave function is much more spread out, and then you have a lower oscillator strength. As you can see, the reduced absorption strength. And at the same time, you see a significant broadening of the peak as well, and that's due to more efficient scattering, because now your exciton is bumping against all these extra electrons, and you have non-radiative decay processes dominating your transitions. So taking these numbers, we basically did like a simple transfer matrix calculation of polarization conversion or reflectivity analysis. And if we look in the complex reflectivity plane, we can see that there's a significant difference in the armchair and zigzag direction. And if we break it down in the amplitude and phase, we can see that we have quite significant differences in amplitude and phase close to the cavity resonance. And I'd like to mention in this case that we are operating in what electrical engineers call impedance matched, or optical scientists would call critical coupling condition, where you basically couple the free space to the cavity in such a way that you have the maximum energy transfer. And that effectively creates like a singularity point at the resonance and gives you a high dynamic range of phase tuning. And that's sort of what we used in this case to get more and more polarization conversion. So now obviously that was not a unique choice of cavity. We can design our cavity at any wavelength by changing the optical spacer. And even without any sort of impedance optimization, you can see that if you look at the 3 Stokes vectors, you can have very nice polarization conversion all throughout the telecom frequency, E, S, and C bands just by changing the spacer thickness. And so we wanted to experimentally test that. Obviously, experimentally, we are kind of limited with fabrication conditions, so we cannot make that nice of a map. So we made a total of 5 representative devices where we spanned PMMA thicknesses, which is our optical spacer. And we saw that we could tune the resonance quite nicely across 100 nanometer bandwidth and get significant polarization conversion as is seen on each of these Poincare spheres as a function of spectrum. So now one question might be is that why is the dynamic range quite different for all of these measurements? And it's mainly related to fabrication issues that we tried to achieve critical coupling for all of these devices, but obviously due to fabrication imperfections, we missed out on a few of them. And so the dynamic range that you see is maybe lower for some of them, but you can nevertheless see quite efficient polarization conversion trajectories for all of these devices. So with this in mind, we basically went on to explore some of the spatial dynamics of these polarization conversion. So this is how our typical devices look like. So in this case, I have an optical image of 3 layers, 6 layers, and bare cavity. And if we look at the hyperspectral imaging of the Stokes vectors or the polarization metrics, so here we have chi, which is the ellipticity, which is basically how much your beam is open or closed, and the azimuthal angle, which is the orientation of your beam. And you can see that outside the cavity, there's this flat response, no response with wavelength or even spatially. But in the black phosphorus, you can see that there is a weak polarization conversion from 6 layers, and there is quite a strong polarization conversion from the 3 layers. But there is quite some dynamic spatially. And we can also kind of map at each pixel what is the outward polarization, and then you can see how the polarization states evolve in terms of the spatial coordinates. And so this is an excellent probe to kind of map these anisotropy distribution. And this relates to the idea of dielectric disorder that exists in most 2D devices. And they come from trapped hydrocarbons, which form during stacking process. And they provide a different dielectric screening to the exciton. And so thus your optical anisotropy gets modified. There also is strain, which is basically the result of the lattice mismatch between black phosphorus and hexagonal boron nitride. Then obviously you can have stacking order differences as well, where your 3 layers might have different stacking within the same flake, and you can get different properties. So at the moment, we're looking more carefully at all of these and trying to see if we can do structural correlation between these polarization conversion states and use some other forms of microscopy, such as Raman, to really see what is the underlying cause of this anisotropy distribution. But nevertheless, this was quite interesting to see in terms of just how polarization conversion evolves as a function of spatial coordinates. So now, as in the previous talk, the speaker mentioned very nicely that MO3 and hexagonal boron nitride and all of these have some sort of anisotropy, and you would expect that there is some also dependence on how you illuminate the system by itself. So you can kind of play with the phase difference and the amplitude between the armchair and zigzag direction in your input conditions, and you can see how the polarization states basically evolve as a function of your spectrum. And you can see that you can have what we like to call a designer chart of polarization states just by tuning the input conditions of the system. And these are all simulated trajectories, and we also experimentally verified that we do indeed get this 180 degrees periodicity in the measurements. So these are azimuthal and elliptical measurements where we did get this exact match with the results that we simulated. And the simulations were actually done to kind of closely match the resonance frequency of this device and the other conditions. But we do have a nice designer platform where we can kind of use the same device to have multiple functionalities by just changing the input conditions. So that's not all. We can also have another trick up our sleeve, which is the idea of tuning it actively by changing the voltage, where we can look at the Stokes vectors as a function of different electron and hole doping. In this case, I'm showing negative voltages or hole doping, but we see similar dynamics in electron doping as well. So if we now look at the evolution of the Stokes vectors, so first we look at the intensity. we see that we have a variation of the coupling. And this is because you're kind of changing the refractive index, so you change your impedance of the system. And so roughly around minus 20 volts, we hit critical coupling. And then as we go away from it, we're off critical coupling. And so if we look at the other three Stokes vectors, which characterize the polarization, you see that this is kind of the most interesting region where you have a lot of dynamics going on. But overall, you can see that there's quite nice tuning in all of these three parameters as a function of doping density. And this is basically saying that as you're changing the optical susceptibility of your system, or BP, it's interacting differently with the cavity, and it's generating all these polarization responses. So if we now visualize these states on the Poincare sphere, we can see that if we operate very close to the cavity resonance, we can have quite a rich dynamics of polarization states. So first of all, we can see that as we change the detuning of the cavity or the wavelength, we have like this tuning in this direction. So that's kind of denoted by the different colors of the results. And then as we change the voltage of the doping density, we can traverse in an orthogonal direction. We can traverse all these polarization states as a function of the doping density. And so over here, I've highlighted the measured polarization states. So you can see that at some wavelengths, we can make it a quarter wave plate as we go from linear to circular. At some wavelengths, we can make it a half wave plate where you go from linear to cross linear. And then obviously you can have other polarization states as well, which is like elliptically polarized states. And so this is like a tremendous dynamic range, because now you can see we're pretty much covering like almost half the Poincare sphere with voltage, and that's pretty much quite a lot for like most applications. And if you now combine this idea with the input tuning, we now basically have a two-dimensional control where we can change the input condition on the device, and we can make the same device electrically function to generate whatever polarization states we want all over the Poincare sphere. Because if you remember from the previous plot of this polarization, you can first of all design your spectral trajectory anywhere on the sphere, and then you can kind of go orthogonal to it with voltage, and thus you can kind of traverse the entire Poincare sphere. So now obviously these were proof of concept measurements and quite interesting findings. We wanted to make it a little more practical because our efficiency of devices were low, and primarily the reason was we worked in critical coupling. So we numerically analyzed some lossless structures where we basically have Bragg mirrors on top and bottom, and we explored how we can kind of play with the coupling of the photon into the system and look at two distinct configurations of the top reflectivity mirrors. And over here we see that we can have very high reflectivity at the inflection point of around 95 or 98%, and we can have a 2π phase shift, which is quite exciting for getting a large polarization inversion between the doped and undoped case for the armchair direction. And again, if we now change the coupling condition by just changing the reflectivity of the top mirror, we can have a so overall the coupling is much weaker, but nevertheless we can have quite high reflectivity all throughout our working wavelength, and then we can still have quite a significant, a little shy of 2π phase shift in these conditions. And one other trick we use in this case to get higher efficiency was taken from the Lipson group at Columbia, where we kind of worked relatively far from the excitonic resonance in order to suppress the losses in the BP itself. So I think taken together, these results are very promising. We're working right now to make more high efficiency structures. We're working to get even higher dynamic range of polarization conversion. But overall, I think this is quite exciting and has provided like some insights into using anisotropic systems or birefringent systems for modulating polarization states of light. So I'd like to conclude by saying that we conceptualized a nanophotonic design for active polarization conversion. We characterized the three-layer black phosphorus and its refractive index as a function of doping, and we were able to integrate that in a resonant cavity, and we demonstrated electrically tunable polarization conversion. So I'd like to thank everyone for their attendance and staying so late in Spain, and I'm happy to take any questions.
Thank you, Seebeck, for the very nice talk and nice results and being on time. So any question from the audience here or in the chat? Okay, so I have one, like how stable are your devices provided that black phosphorus is very degradable environmentally?
Yeah, so that's actually a challenge we faced in a lot of our fabrication. All of this fabrication had to be done in a glove box. But what we found that when we encapsulate these layers all within the glove box with hexagonal boron nitride, we measured all of these devices over a period of 1 year or 8 months, and we saw no degradation in performance with multiple rounds of measurements and voltage tuning. So once we encapsulate them, they're quite stable.
Also, I think black box phosphorus is in plane elliptic, right? So have you considered any other more anisotropic material, like in plane hyperbolic or with like strong anisotropy for your device?
So if I understand correctly, you're asking if we looked at other materials or?
Anisotropy of black phosphorus, it's in plane elliptic, right?
Yeah. I'm not sure I follow the question. Can you repeat the question?
Yeah, so what is the anisotropy of your material? Because you need it to be birefringent, right?
Mm-hmm. Mm-hmm.
So what kind
So
of
you're asking what is the
anisotropy
mechanism of the birefringence?
or if you have considered more anisotropic materials for future studies?
Oh yeah. So yeah, so first of all, like I think like this kind of opens like kind of a new direction for people to look at birefringent systems. So I guess so far people have been looking at say anisotropic systems with respect to say polaritons, where they look at hyperbolic polaritons and they see the propagation. One of the challenges of using say things like HBN and molybdenum trioxide is that those are basically phonon driven birefringent systems. So it's very hard to kind of electrically tune those transitions or those susceptibilities. But nevertheless, those are very interesting materials to look at if you integrate in a cavity. In fact, there's some work from Northwestern University where they looked at molybdenum trioxide and its ability to convert polarization. One other anisotropic system, which is quite interesting electronically, is rhenium disulfide, which is also similar to black phosphorus. It has like quite different excitonic properties in its different axes. And that's also something that I think can be quite interesting to look at. I'm not sure I answered your question correctly.
Yeah, sure. Yeah, sure. Thank you very much for your answer. And I think it's already time for the break. So yeah, thank you all for your attendance, and let's meet in the poster session in like 10 minutes.